Have you ever gazed up at the night sky and wondered if, somehow, it might be gazing back at you? Not with eyes or consciousness as we understand it, but through the infinite reflections it holds, the eternal echoes it preserves, and the ancient light it carries across the vastness of time. The night sky is far more than just a canvas decorated with distant stars. It is a living memory, a cosmic mirror, a silent witness to everything that has ever been. Tonight, as you drift towards sleep, we will explore the fascinating idea of a universe that is not merely expanding outward into darkness, but one that reflects inward upon itself, creating patterns, preserving echoes, and carrying light across billions of years. This is the story of the sky that looked back at itself, a gentle journey through cosmic wonder that will carry you into peaceful dreams beneath the stars that have watched over us since the very beginning of time. Imagine the fabric of the universe as an immense cosmic mirror, not made of glass and silver, but of space and time itself. This extraordinary mirror doesn't simply reflect light in the way we're familiar with. Instead, it bends, warps, and transforms energy as it travels across the cosmic expanse. Every photon of light, every gravitational wave, every particle that moves through space carries with it a story and imprint of where it has been and what it has encountered on its journey. When we look at galaxies millions of light years away, what we're seeing is not just their direct light, but often their gravitational influence acting as enormous cosmic lenses. These galaxy-sized magnifying glasses reveal distant light that would otherwise remain forever hidden from our view. A single galaxy can split the light from objects behind it, creating multiple images of the same distant star, or even multiplying an entire galaxy into a cosmic illusion of 4 or 5 identical twins, arranged in a perfect cross or circle. The universe preserves echoes of its own shape in ways that continue to astonish astronomers. Consider how the largest structures in our cosmos formed vast clusters of galaxies arranged in filaments and sheets, with enormous voids between them. This cosmic web wasn't randomly constructed. It grew from tiny ripples in the density of the early universe, ripples that have been magnified across billions of years until they became the framework upon which galaxies themselves are strung like pearls on an invisible necklace. When light travels through this cosmic web, it doesn't move in straight lines. It curves around massive objects, sometimes taking multiple paths to reach us. This means that the same distant object might send its light to us along several different routes through space, arriving at different times. In this way, the universe doesn't just show us one version of a distant galaxy, it shows us multiple perspectives, multiple moments in time, all arriving at our telescopes, as if the cosmos itself were trying to provide us with a more complete picture. Even the darkness between stars is part of this reflection. The seemingly empty regions of space are filled with dust and gas that absorb and scatter light, creating the dark nebulae that appear as holes in the brilliant star fields. These clouds don't simply block our view, they process the light that passes through them, absorbing certain wavelengths and scattering others, turning the light of distant stars into information about the cloud's own composition and structure. The universe mirrors itself most fundamentally in its symmetries, the ways in which its laws remain constant when viewed from different perspectives. A galaxy spinning clockwise looks the same as one spinning counterclockwise when viewed in a mirror. The forces that bind atoms together work the same way, regardless of where in the universe those atoms might be. These symmetries are like reflections across the dimensions of reality itself, showing us that the cosmos follows patterns that repeat and echo across its vast expanse. Perhaps most wonderfully, the universe reflects itself through us. The atoms in our bodies were forged in the hearts of ancient stars, scattered across space when those stars exploded, only to be gathered again into planets and eventually into living things. We are, in the most literal sense, the universe looking back at itself, stardust that has arranged itself into beings capable of wondering about the stars. But the reflection extends far beyond our own existence. Consider black holes, those regions of space where gravity is so intense that not even light can escape. At first glance, these might seem like cosmic dead ends, places where information simply vanishes, yet black holes reflect the universe in their own way. Around their boundaries, they warp space-time itself, bending light into rings and arcs that reveal what lies behind them. And in their behavior, they reflect the fundamental nature of space and time, showing us how these seemingly separate aspects of reality are actually woven together into a single fabric. Through the phenomenon known as Hawking radiation, black holes even reflect information about what they've consumed, slowly radiating it back to the universe over unimaginable spans of time. Nothing truly disappears in our universe, it merely transforms, transferring its information from one form to another. In this way, black holes become another kind of cosmic mirror, preserving and eventually returning the light they capture. The reflection of the universe is also visible in how galaxies arrange themselves over time. They don't simply drift apart as the universe expands. Instead, they form clusters and superclusters, drawn together by their mutual gravitational attraction. These structures create a map of invisible dark matter, a substance we cannot directly observe, but whose presence we can infer from how it shapes the visible universe. The galaxies become like floating lanterns, illuminating the underlying structure of a river we cannot otherwise see. When two galaxies collide, they pass through each other in slow motion, their stars rarely crashing together due to the vast emptiness between them. But their gas clouds interact, compressing and triggering the birth of new stars. In these collisions, galaxies reflect each other's structure, exchanging material and energy in a cosmic dance that can last for billions of years. The end result is often a new, merged galaxy that bears the imprints of both its parents, another way the universe preserves its own history. The most profound mirrors in the cosmos may be the ones we've only recently discovered: gravitational waves. These ripples in space-time are created when massive objects accelerate, and they travel outward at the speed of light, carrying information about the events that created them. When two black holes spiral together and merge, the gravitational waves they generate contain a perfect record of their dance, their masses, their spins, the shape of their orbit. These waves pass through everything in their path, barely interacting with matter, preserving their message across billions of light years. Our instruments can now detect these whispers from the most violent events in the universe, translating them into sounds we can hear. The chirp of merging black holes, the rumble of colliding neutron stars, these are the echoes of events that happened long ago and far away, preserved in the very fabric of space itself. The universe not only reflects light, it reflects its own structure through the ripples in its foundation. Water on Earth reflects the sky above it, creating a doubled image of clouds and stars. Similarly, the distribution of galaxies in space reflects the underlying density of the early universe. Regions that were slightly denser than average became the seeds of today's galaxy clusters, while less dense regions evolved into the vast cosmic voids. The pattern we see today is like a vastly magnified reflection of conditions that existed when the universe was just a fraction of a second old. This mirror stretches across time as well as space. The light from the most distant objects we can see has been traveling for almost the entire age of the universe. It carries information about how galaxies formed and evolved, how the first stars ignited in the darkness, how the universe transformed from a hot, opaque fog into the transparent cosmos we inhabit today. Each era of cosmic history is preserved in light of different distances, creating a layered reflection that astronomers can read, like the rings of an ancient tree. The universe even reflects itself in its expansion. As space stretches, it carries galaxies away from each other, but not in a chaotic manner. The pattern of recession follows a remarkably simple rule. The farther a galaxy is from us, the faster it appears to be moving away. This relationship, known as Hubble's law, reflects a fundamental truth about our cosmos, that the expansion is happening everywhere, with each region of space stretching like the surface of an inflating balloon. Even more remarkably, this expansion is accelerating, driven by a mysterious force we call dark energy. The universe not only reflects its past in the light that reaches us, it reflects its future in the increasing rate of expansion. By studying how galaxies move away from each other, astronomers can project forward, predicting the ultimate fate of our cosmic home, a future of ever-increasing isolation as galaxies disappear beyond our cosmic horizon, their light stretched and dimmed until it can no longer reach us. The oldest light in the universe, the cosmic microwave background radiation, provides perhaps the most perfect mirror of the cosmos. This faint glow, visible in all directions, is the remnant of the hot, dense state in which the universe began. It shows us the universe as it was just 380, 0 years after the Big Bang, when the first atoms formed and light could finally travel freely through space. The tiny variations in this radiation reflect the seeds of all the structure we see today, the first gentle ripples that would eventually grow into galaxies and galaxy clusters. On the smallest scales, quantum mechanics reveals another way the universe mirrors itself. Particles can become entangled, linking their properties across vast distances. Change the state of one particle, and its entangled partner instantaneously reflects that change, no matter how far away it might be. This spooky action at a distance, as Einstein called it, suggests a deep interconnectedness in the fabric of reality, a cosmic mirror that operates beyond the constraints of space and time as we understand them. The reflection extends to the very laws that govern the cosmos. The equations of physics often show a property called time reversal symmetry. They work equally well whether time flows forward or backward. This symmetry reveals a profound truth. At the fundamental level, the universe doesn't distinguish between past and future in the way we do. The arrow of time, that we experience the fact that eggs break but never unbreak, that coffee cools but never spontaneously heats emerges from the statistics of countless particles interacting, not from the basic laws themselves. Even the elements reflect the history of the universe. Hydrogen and helium were forged in the first minutes after the Big Bang, while heavier elements like carbon, oxygen, and iron were created much later, in the nuclear furnaces of stars. The gold in a wedding ring was likely created when 2 neutron stars collided billions of years ago, sending a spray of heavy elements into space. Our planet, our bodies, everything we touch all contain atoms that reflect different chapters in the cosmic story. The universe reflects itself in cycles as well as in moments. Stars form from collapsing clouds of gas, shine for millions or billions of years, and then return their material to space when they die, sometimes gently, as planetary nebulae, sometimes violently, as supernovae. This recycled stardust then becomes part of new stars and planets, carrying forward the legacy of previous stellar generations. Nothing is wasted. Everything is transformed and reused. The shapes of galaxies reflect their histories. Spiral galaxies like our Milky Way reveal a past relatively free from major collisions, allowing their stars to settle into orderly rotating disks. Elliptical galaxies, rounder and less structured, often form from the mergers of spirals, their chaotic shapes reflecting the violent encounters that created them. Irregular galaxies show signs of ongoing interactions with their neighbors, their distorted forms, a testament to the gravitational forces reshaping them. Even the emptiness of space is a kind of mirror. According to quantum field theory, vacant space is anything but empty. It seethes with virtual particles that pop in and out of existence, borrowing energy from the vacuum for brief moments before returning it. These quantum fluctuations reflect the underlying energy of nothingness itself, showing us that emptiness has structure, that absence has presence. Perhaps the most profound reflection of all is consciousness, the fact that within this vast, ancient universe, arrangements of matter have emerged that are capable of contemplating their own existence. We are the eyes through which the universe sees itself, the mind through which it comes to know itself. Every observation we make, every discovery about distant galaxies or subatomic particles, is the universe reflecting upon its own nature. In our telescopes, we see light that has traveled for billions of years, carrying images of galaxies as they were when Earth was young or before it even existed. In our particle accelerators, we recreate conditions that haven't existed naturally since the first seconds after the Big Bang. Through mathematics, we describe patterns and relationships that seem woven into the very fabric of reality. Through art and music, we express our wonder at the beauty and mystery of existence. These human activity escience, mathematics, are themselves reflections, ways of mirroring the universe in forms we can understand and share. The equations of general relativity reflect the curvature of space-time. The periodic table reflects the patterns in how atoms are structured. A symphony reflects the mathematical relationships between frequencies that we perceive as harmony. A painting of a starry night reflects both the light from distant suns and the emotional response that light evokes in us. The universe mirrors itself through these nested levels of reflection. Physical laws create structures. Structures enable life. life evolves consciousness. Consciousness discovers the physical laws. The circle closes. The reflection becomes recursive. The universe, looking at itself, a cosmic hall of mirrors stretching across billions of light years and billions of years of time. Yet this reflection is always incomplete, always in process. We see only a fraction of what exists, limited by our instruments, by the speed of light, by the cosmic horizon, beyond which information can never reach us. The universe we observe is just one reflection, one perspective on a reality that may be far stranger and more wonderful than we can imagine. Like a mirror that can never show its own back, the universe may contain aspects that are fundamentally inaccessible to us. Other universes might exist beyond our own, other dimensions, other forms of matter and energy that don't interact with what we can detect. The reflection we see is just one facet of a cosmic jewel with potentially infinite faces. But in the reflection we can see, there is wonder enough to last many lifetimes. The universe shows us its history written in light, its structure encoded in the dance of galaxies, its future hinted at in the accelerating expansion of space. It shows us deep connections between the very large and the very small, between the beginning of time and the world we inhabit now. As you drift towards sleep, imagine yourself as part of this grand cosmic mirror, a collection of atoms that originated in ancient stars, assembled into a form capable of wondering about those same stars. The universe has shaped you, and through your awareness, you shape your understanding of the universe. In this mutual reflection lies a profound connection, a belonging that transcends our brief moments in time. The universe as a mirror doesn't just show us what exists, it reveals relationships, patterns, and meanings. It shows us our place in the cosmic story, not as passive observers, but as active participants in the universe's long journey of self-discovery. In the depths of the night sky, we find not just distant points of light, but reflections of the very processes that created us and everything we know. When you look up at the night sky, you're not seeing stars as they are now, but as they were when their light began its journey to your eyes. That brilliant blue star Sirius? You're seeing it as it was 8.5 years ago. The orangish glow of Betelgeuse in the constellation Orion shows you how that star appeared over 600 years in the past. The Andromeda Galaxy, visible as a faint smudge to the naked eye on dark nights, appears to us as it was 2.5 million years ago, when our earliest human ancestors were just beginning to walk the plains of Africa. This simple fact that light takes time to travel transforms our view of the cosmos into something far more profound than a mere snapshot. What we call now in the universe is an illusion. There is no universal present moment that connects you to distant stars and galaxies. Instead, looking outward into space is literally looking backward through time. The stars overhead form a three-dimensional time capsule surrounding Earth. The closest stars show us their appearance from years or decades ago, while the most distant objects visible to our unaided eyes represent centuries or millennia past. With telescopes, we extend this temporal voyage deeper, observing galaxies billions of light years away, effectively witnessing them as they were billions of years ago, not long after the universe itself began. This cosmic time machine creates a strange symmetry. If there are observers on planets circling stars 100 light years from Earth, they would currently see our world as it was in 1925. They might witness the flickering lights of our first electric cities, but would have no idea of our current civilization. If we could somehow instantaneously teleport to their world and look back at Earth through their telescopes, we would see our own past. Reflections of light stretch across truly cosmic distances. Consider the light from the most distant galaxies we can observe, galaxies so remote that their light has been traveling to us for over 13 billion years. These ancient photons began their journey when the universe was less than 1 billion years old. They've traveled through space as it expanded, witnessed the formation of galaxy clusters and superclusters, and finally, after an almost unimaginable journey, entered our telescopes to form images of the infant universe. These ancient messengers carry within them the history of cosmic evolution. By studying light from different distances, and therefore different times, astronomers have pieced together the story of how galaxies formed and matured. Early galaxies were smaller, more irregular, and forming stars at a furious pace. As we look at progressively closer galaxies, we see them settle into the majestic spirals and ellipticals that populate the universe today. The light itself changes during its journey across the expanding universe. As space stretches, the wavelength of light traveling through it stretches too. This cosmic redshift transforms the original colors of distant galaxies, shifting their light toward the red end of the spectrum. The more distant the galaxy, the greater the redshift. By measuring this effect, astronomers can determine not just how far away these galaxies are, but how much the universe has expanded since their light began its journey to us. This stretching of light waves creates another kind of reflection, direct link between the present state of the universe and its earlier, more compact form. The cosmos carries within it the echoes of its own expansion, written in the shifted wavelengths of light that reach us from different distances. Sometimes, the universe offers us even more complex reflections across time. When massive objects like galaxy clusters bend light from objects behind them, they can create multiple images of the same distant galaxy. These images don't just show the same object from different angles, they often show it at different moments in time. Light following different paths around the gravitational lens can take longer or shorter routes to reach us, creating a time delay between the multiple images. In some cases, astronomers have witnessed supernovae appear in one image of a lensed galaxy and then, months or years later, see the same explosion appear in another image. These cosmic time delays give astronomers a unique opportunity. By measuring the differences in arrival time between multiple images, they can calculate the expansion rate of the universe with remarkable precision. The cosmos not only reflects light through space but staggers its arrival in ways that reveal fundamental truths about the universe's growth. The reflections of light across time aren't limited to distant galaxies. Within our own Milky Way, vast clouds of dust and gas reflect the light of nearby stars, creating the glowing regions we call reflection nebulae. The blue light scattered by dust particles in the Pleiades star cluster has been traveling for only a few decades before reaching Earth, a cosmic eye blink compared to the billion-year journeys of light from distant galaxies, but still a window into the recent past of our galactic neighborhood. Even closer to home, the light reflecting off the planets in our solar system carries information about events separated from us by minutes or hours. The sunlight bouncing off Jupiter takes nearly 45 minutes to reach Earth. If we could somehow observe Jupiter with enough detail, we would see weather patterns that had already evolved by the time their light reached our telescopes. The Moon offers perhaps the most familiar reflection across time, though the delay is merely 1.3 seconds the time it takes light to cross the 250,000 miles between Earth and its satellite. When Apollo astronauts walked on the lunar surface, their radio communications faced this same delay. Each word spoken on the Moon traveled to Earth at the speed of light, creating a brief but noticeable pause in conversations between astronauts and mission control. This ever-present delay in our perception of the universe has profound implications. It means we never see things as they are, only as they were. The star that exploded 1,000 years ago might appear perfectly normal in our telescopes tonight if its light hasn't had time to bring us news of its catastrophic end. Conversely, a star whose light shows us a supernova might have already collapsed into a neutron star or black hole by the now that we can never directly perceive. These reflections across time create a kind of cosmic uncertainty. The universe we observe is always a historical universe, never the contemporary one. And the further we look, the more ancient the history we witness. Our knowledge of the cosmos is always incomplete, always catching up to a reality that has already moved forward. Yet there's a symmetry to this limitation. Just as we see distant objects as they were in the past, any hypothetical observers in those distant galaxies would see Earth as it was in their past. If we could somehow place a perfect mirror 30 light years from Earth, then aim our telescopes at it, we would see reflections of our own planet as it was 60 years ago, the time it takes light to make the round trip. The universe creates natural time capsules through these reflections, preserving images of earlier states across vast distances. Sometimes, these reflections create ghostly echoes of dramatic cosmic events. When massive stars explode as supernovae, they often produce intense bursts of light that radiate outward. If this light encounters dust clouds in its path, some of it may be reflected toward Earth, arriving years or decades after the direct light from the explosion. Astronomers call these delayed reflections light echoes. By studying them, researchers can effectively see the same explosion from different angles and at different times, building a more complete picture of these cataclysmic stellar deaths. Light echoes have allowed astronomers to study historical supernovae long after their initial brilliance faded. The explosion that created the Cassiopeia A supernova remnant likely occurred around 1680, but wasn't observed directly from Earth. Centuries later, astronomers detected light from this explosion reflecting off distant dust clouds, giving them a chance to study an event that human observers missed when it originally occurred. The universe had preserved a reflection of this spectacular stellar death across both space and time. Similar echoes can occur with other bright cosmic events. Quasars, the extraordinarily luminous cores of distant galaxies powered by supermassive black hole scan, vary in brightness over time. When this changing light illuminates gas clouds surrounding the quasar, it creates a kind of three-dimensional echo that travels outward at the speed of light. By measuring the time delay between changes in the quasar's direct light and the corresponding changes in the light reflecting off these clouds, astronomers can map the environment around these powerful cosmic engines. The reflections of light across time reveal another fascinating aspect of our universe. It has a definite age. Because light travels at a finite speed, there's a limit to how far back in time we can see. This cosmic horizon represents the greatest distance from which light has had time to reach us since the beginning of the universe. Currently, this horizon sits at about 46.5 billion light-years away, much farther than the 13.8 billion years the universe has existed because of the expansion of space itself. Beyond this horizon lies the truly unknown regions of the universe, from which light simply hasn't had time to reach us yet. Each day, photons from slightly farther away complete their journey to Earth, gradually expanding our view of the cosmos. The universe is revealing itself to us one light-year at a time, as reflections from increasingly distant regions finally arrive at our doorstep. This gradual unveiling creates an interesting possibility. If the universe is infinite, or even just much larger than the part we can currently observe, then the cosmic horizon acts as a kind of one-way mirror. We cannot see beyond it, but regions beyond our horizon might someday be able to see us, as our light eventually reaches them. The reflection of Earth carrying images of our oceans, continents, and civilizations continues its outward journey, even to regions from which we can receive no corresponding message. The finite speed of light not only limits our view of distant space, but also constrains our understanding of cosmic events as they unfold. When astronomers observe events in nearby galaxies, they're seeing them almost as they happen, with delays of only millions of years. But when observing the same phenomena in the most distant galaxies, they're seeing these events as they occurred in the universe's infancy, potentially before many physical processes had reached their current state. This cosmic time dilation creates a natural laboratory for studying how the universe and its contents have evolved. By comparing similar objects and events at different distance ends, and therefore different times, astronomers can track changes in everything from the rate of star formation, to the composition of galaxies, to the expansion rate of space itself. The reflections of light across time also reveal the changing nature of the universe itself. The cosmos today is very different from what it was billions of years ago. It's cooler, less dense, more structured, and expanding at an accelerating rate. The most distant light reaching us shows a universe that was hotter, denser, and more chaotic. These ancient photons carry the imprint of their origin time, reflecting not just distant objects but distant cosmic ages. In a very real sense, the night sky is like a vast museum of cosmic history, with exhibits arranged by their distance from Earth. Nearby galaxies show us relatively recent cosmic history, while the most distant objects visible to our telescopes display conditions from billions of years ago. Between these extremes lie galaxies from every era, their light carrying information about how the universe changed over time. This cosmic museum isn't static, it's constantly updating as new light arrives from increasingly distant regions. Each photon that enters our telescopes brings new information, adding detail to our understanding of cosmic history. The universe is continually showing us more of itself, reflecting its past into our present. Perhaps the most profound reflection across time comes from the cosmic microwave background radiation, the faint afterglow of the Big Bang itself. This ancient light has been traveling for 13.8 billion years. carrying information about the universe when it was just 380 years old. By studying the subtle patterns in this radiation, astronomers can see reflections of the tiny density fluctuations that eventually grew into all the structure we see today: galaxies, clusters, and the vast cosmic web. This primordial light represents the oldest reflection we can detect, a baby picture of the universe, showing its features when it was less than 0.003% of its current age. The fact that we can observe this ancient light at all is remarkable. It means the universe has preserved a direct reflection of its own birth, carrying it across almost 14 billion years to reach our instruments today. The reflections of light across time aren't just passive records, they actively shape our understanding of cosmic evolution. By comparing objects at different distances, astronomers can construct timelines showing how galaxies merged and grew, how star formation rates changed, how the chemical composition of the universe evolved as successive generations of stars fused hydrogen into heavier elements. These light-borne reflections have revealed surprising aspects of cosmic history. For instance, astronomers discovered that the expansion of the universe isn't slowing down as expected, but accelerating, a finding so unexpected that it earned its discoverers the Nobel Prize in Physics. This acceleration began roughly 5 billion years ago, meaning that while the most distant light shows us a universe whose expansion was slowing due to gravity, light from closer galaxies reveals the more recent era of accelerating expansion. Even the colors of distant galaxies reflect changes across cosmic time. The earliest galaxies formed stars at a furious pace, burning hot and blue. As the universe aged, star formation slowed in many galaxies, and their stellar populations aged from blue to yellow to red. By observing galaxies at different distances, astronomers can track this evolution from youthful blue systems to mature redder ones. Light's journey across time doesn't just reveal the evolution of stars and galaxies, it also shows us changes in the space between them. The early universe was filled with a fog of neutral hydrogen that blocked certain wavelengths of light. As the first stars and galaxies formed, their radiation gradually ionized this fog, making the universe transparent. By studying light from progressively more distant quasars, astronomers can see exactly when and how this transition occurred, another reflection of a pivotal moment in cosmic history preserved in the light reaching us today. The reflections we observe aren't limited to electromagnetic radiation. In recent years, astronomers have detected gravitational waves ripples in space-time, created by violent cosmic events like merging black holes. These waves travel at the speed of light, carrying information about events that may have occurred billions of years ago. Like light, they create reflections across time, showing us echoes of ancient collisions that reshaped space itself. When observed together, gravitational waves and light can provide complementary reflections of the same event. In 2017, astronomers detected gravitational waves from merging neutron stars and, simultaneously, observed the electromagnetic radiation produced by this collision. These different messengers traveled across 130 million light-years of space, each carrying unique information about the same cosmic moment, preserved across time until they reached our detectors. As technology advances, we continue to develop new ways of seeing these reflections across time. Telescopes operating across the electromagnetic spectrum from radio waves to gamma rays reveal different aspects of distant objects. Neutrino detectors catch particles that, like light, travel at cosmic speeds and bring us information from distant events. Gravitational wave observatories sense the faint ripples in spacetime from cataclysmic mergers. Each of these cosmic messengers reflects a different aspect of the universe's story, preserved across the vast gulfs of time and space. Together, they create an ever more complete picture, not just of what the cosmos contains, but of how it has changed and evolved throughout its long history. As you drift towards sleep tonight, remember that the starlight entering your window has crossed years, centuries, or millennia of space to reach you. Each star is a time capsule, each galaxy a reflection from a different era. The universe surrounds us not just with space, but with time itself, visible and tangible in the ancient light that continues its long journey across the cosmos. The night sky is not just a display of distant objects, it's a mirror reflecting different epochs of cosmic history simultaneously. In its depths, we see the universe not as a static entity, but as a dynamic, evolving system. constantly changing yet preserving reflections of its earlier states in the light that travels endlessly through the darkness between the stars. Chapter 3. The Cosmic Microwave Background's Silent Memory. Of all the light in our universe, none has traveled further or carries a more profound story than the faint, almost imperceptible glow that fills every direction of the sky. This ancient radiation, invisible to our eyes but detectable by specialized instruments, is called the Cosmic Microwave Backgrounder, CMB. It is, quite literally, the oldest light in existence, a fossil of radiance from when the universe was in its infancy, just 380 years old. Imagine for a moment what it means to detect photons that have been traveling for 13.8 billion years light that began its journey when the universe was less than 1,000th of its current age. These ancient messengers have crossed almost the entire observable universe to reach us, carrying with them information preserved since the cosmos was still glowing hot from the Big Bang. The discovery of this primordial light was one of the greatest scientific achievements of the 20th century, and it happened almost by accident. In 1964, two astronomers at Bell Laboratories, Arno Penzias and Robert Wilson, were testing a sensitive microwave antenna designed for satellite communications. No matter where they pointed their instrument, they detected a persistent background, noisy, a faint hiss that seemed to come from every direction in the sky. At first, they suspected this noise might be the result of equipment malfunction or even pigeon droppings on their antenna. But after exhausting every possible explanation, they realized they had stumbled upon something extraordinary: radiation left over from the birth of the universe itself. For this serendipitous discovery, Penzias and Wilson would later receive the Nobel Prize in Physics. What makes the cosmic microwave background so significant is that it represents the moment when light was first able to travel freely through space. Before this time, the universe was so hot and dense that photons couldn't move far before colliding with electrons in the superheated plasma that filled all of space. The cosmos was opaque, like a dense fog that scatters light in all directions. But as the universe expanded and cooled, protons and electrons eventually combined to form neutral hydrogen atoms, a process scientists call recombination. Without free electrons to scatter them, photons could suddenly travel unimpeded. The universe became transparent, and light was liberated to begin its journey across the cosmos. This transition from an opaque to a transparent universe happened everywhere at roughly the same time. The photons released during this era have been traveling ever since, stretched by the expansion of space from visible light to microwave radiation. When we detect this ancient light today, we are seeing the universe as it appeared at the moment of recombinatione, moment that astronomers sometimes call the surface of last scattering. What's remarkable about the cosmic microwave background is its extraordinary uniformity. No matter which direction we look, its temperature is almost exactly the same, about 2.7 degrees above absolute zero. This remarkable consistency tells us something profound about the early universe. Despite the clumpy, structured cosmos we see today, with its galaxies, clusters, and vast cosmic voids, the infant universe was incredibly smooth and homogeneous. But the key word here is almost. When scientists made more precise measurements of the CMB in the 1990s using the COBE satellite, they discovered something extraordinary: tiny variations in temperature, differences of just 1 part in 100, 0. These minute fluctuations might seem insignificant, but they are of cosmic importance. They represent the seeds from which all structure in the universe would eventually grow. These tiny temperature variations in the CMB are like fossilized noise, the frozen imprint of quantum fluctuations that existed in the incredibly early universe and were then stretched to cosmic scales during a period of rapid expansion called inflation. Areas with slightly higher temperatures represent regions of slightly higher density places, where gravity would eventually pull matter together to form galaxies and clusters billions of years later. By mapping these temperature variations with increasing precision, missions like WMAP and Planck have created detailed portraits of the infant universe. The patterns they reveal tell us about the composition of the early cosmos, the rate of its expansion, and even its ultimate fate. The CMB has become our most important window into cosmic history, a memory of the universe preserved in light that has crossed almost the entire observable cosmos to reach us. The CMB doesn't just tell us about the universe's past, it also reveals its composition in exquisite detail. By analyzing the precise pattern of temperature fluctuations, cosmologists can determine that ordinary matter, the stuff of planets, stars, and people, makes up only about 5% of the universe. About 27% consists of dark matter, which interacts through gravity, but not through other forces. The remaining 68% is dark energy, the mysterious force driving the accelerating expansion of the universe. This cosmic census, derived from the ancient light of the CMB, represents one of the most profound discoveries in modern science. The vast majority of our universe consists of substances that we cannot directly see or touch, whose nature remains one of the greatest mysteries in physics. Yet their influence is written in the subtle patterns of this primordial radiation, allowing us to detect their presence across billions of years of cosmic history. The CMB also preserves information about the geometry of space itself. By measuring the typical size of the temperature fluctuations, cosmologists can determine whether space is curved like a sphere, saddle-shaped, or flat. Their conclusion? To remarkable precision, our universe appears to be flat. Its geometry follows the rules of Euclidean geometry we learn in school. This flatness suggests that the universe is finely balanced between eternal expansion and eventual collapse, poised on a knife edge that requires explanation. Perhaps most remarkably, the cosmic microwave background contains imprints of sound waves that traveled through the early universe. In the primordial plasma before recombination, pressure waves, essentially sound waves, moved through the hot gas, creating regions of compression and rarefaction. When the universe became transparent, these sound waves were frozen in place, preserved as subtle patterns in the CMB that we can detect today. By analyzing these acoustic oscillations, scientists can determine fundamental properties of the cosmos, including its age, expansion rate, and composition. The early universe was, in a very real sense, a vast musical instrument, resonating with deep, fundamental tones far below the range of human hearing. Those ancient cosmic melodies are still detectable, encoded in the temperature variations of the CMB. The cosmic microwave background is not completely uniform. In another way, it exhibits a slight temperature difference depending on which direction we look. One half of the sky appears slightly warmer than the opposite direction. This dipole pattern isn't a feature of the early universe, but rather the result of our own motion through space. As Earth moves within our galaxy, and our galaxy moves within our local group of galaxies, and our local group moves within the larger cosmic web, we create a kind of Doppler effect in the CMB, making it appear slightly warmer in the direction we're moving toward and cooler in the direction we're moving away from. By measuring this dipole pattern, astronomers can determine our motion relative to the CMB itself, essentially, our motion relative to the overall framework of the universe. We're moving at about 600 kilometers per second toward a point in the constellation Centaurus. This cosmic drift is the combined result of Earth's orbit around the Sun, the Sun's orbit around the galactic center, our galaxy's motion within the local group, and the local group's movement within the larger supercluster. Beyond these large-scale patterns, the CMB also contains more subtle signatures. Scientists have detected polarization in the ancient lighter, faint alignment in the orientation of its electromagnetic waves. This polarization arose when CMB photons scattered off electrons just before the universe became transparent, and it provides another rich source of information about conditions in the early cosmos. One specific type of polarization pattern, known as B-modes, is particularly sought after. These swirling patterns could provide evidence of primordial gravitational waves ripples in space-time, generated during the inflationary epoch in the first fraction of a second after the Big Bang. Detecting these polarization patterns would give us a window into the physics of inflation and potentially provide evidence for the unification of forces at energies far beyond what any particle accelerator could achieve. The cosmic microwave background also reveals information about what happened after it was created. As its photons traveled across the cosmos, they sometimes passed through clouds of hot gas in galaxy clusters. When CMB light encounters these clouds, its photons can gain energy from interactions with high-energy electrons, slightly changing the spectrum of the radiation in a process called the Sunyaev-Zeldovich effect. By measuring these subtle spectral distortions, astronomers can detect galaxy clusters even when they're too faint or distant to be seen directly. The ancient light of the CMB becomes a backlighting tool, revealing structures that formed billions of years after the CMB itself was created. In this way, the oldest light in the universe helps us map some of the most massive structures that evolved long afterward. The CMB also interacts with the large-scale gravitational field of the universe. As its photons travel through space, they're subtly deflected by the gravitational pull of matter, both visible and dark, in a process called gravitational lensing. By carefully analyzing the patterns in the CMB, scientists can detect these deflections and create maps of the distribution of matter between us and the surface of last scattering. This gravitational lensing of the CMB provides yet another way to probe the distribution of dark matter and the evolution of cosmic structure. It's as if the universe has provided us with both an ancient backdrop and the means to see how that backdrop is distorted by everything that lies between it and use another layer of cosmic memory preserved in this primordial light. The precision with which we can measure the cosmic microwave background continues to improve with each generation of instruments. Ground-based observatories in Antarctica and Chile's Atacama Desert, balloon-borne experiments flying at the edge of space, and space missions like Planck have mapped the CMB with ever-increasing sensitivity. Each improvement reveals new details about the early universe and constrains cosmological theories with greater precision. Future CMB observations may help resolve some of the most pressing questions in modern cosmology. Did inflation theorize period of ultra-rapid expansion in the universe's first fraction of a second actually occur? If so, what caused it? Are there signs of cosmic string hypothetical one-dimensional defects in spacetime imprinted in the CMB? Does the pattern of temperature fluctuations show any evidence for physics beyond our standard models? The cosmic microwave background may even contain clues about what existed before the Big Bang. Some theories suggest that our universe might be part of a larger multiverse, with our Big Bang representing just one of many cosmic origins. If our universe collided with another one in its early history, this interaction might have left detectable signatures in the CMB circular patterns that could be evidence of these cosmic collisions. The CMB represents a boundary in our cosmic vision. We cannot directly observe light from earlier times because the universe was opaque. However, other forms of radiation might someday allow us to peer even further back. Primordial gravitational waves could carry information from the inflationary epoch itself, while cosmic neutrinos might someday be detected from when the universe was just 1 second old. For now, though, the cosmic microwave background remains our clearest window into the infant universe, a silent memory of a time when the cosmos was still young. Its photons have traveled for 13.8 billion years, crossing nearly the entire observable universe to reach our detectors. They've passed through the vast cosmic web, witnessed the formation of galaxies and clusters, and carried their ancient message across time to the present day. In the patterns of this ancient light, we find evidence of quantum fluctuations stretched to cosmic scales, acoustic oscillations frozen in time, and the seeds of all the structure we see today. We find a census of the universe's contents and a measurement of its geometry. We find our own motion through space and the gravitational influence of everything between us and the edge of the observable universe. Most profoundly, we find a connection to our cosmic origins. The atoms in our bodies were once part of the same primordial plasma that created the CMB. We are made of the same substance that once filled the entire universe, now evolved and arranged into complex patterns capable of detecting and understanding the light from that ancient time. The cosmic microwave background is more than just radiation, it's a memory preserved in light, a message from the beginning of time. It reminds us that the universe was once very different from what it is today, yet the seeds of everything we know were already present. It tells us that the cosmos has a history, a beginning that we can study and understand, even from our remote vantage point billions of years later. As you drift towards sleep tonight, consider this remarkable fact. The room around you is filled with photons that have been traveling since the universe was young. These ancient messengers pass through your body every second, carrying their 13.8 billion-year-old information. The memory of cosmic dawn surrounds us constantly, silent witnesses to the greatest story ever told, the evolution of our universe from its hot, dense beginnings to the vast, complex cosmos we inhabit today. The cosmic microwave background's silent memory connects us to our deepest origins. It reminds us that we are not separate from the cosmos, but part of its ongoing story. The same physical processes that created and shaped this ancient light also led, through billions of years of cosmic evolution, to planets, life, and consciousness itself. In studying the CMB, we study not just the universe's past, but the foundations of our own existence. This ancient light will continue its journey long after our brief lives have ended. It will pass through space that expands ever faster under the influence of dark energy. Billions of years from now, when the stars of our galaxy have burned out and the universe has grown cold and dark, these photons will still carry their message across an increasingly empty cosmosa memory of a time when the universe was young, hot, and filled with possibility. The cosmic microwave background stands as testimony to an extraordinary fact: the universe remembers its own beginning. In the subtle patterns of this ancient radiation, the cosmos has preserved a record of its earliest moments, a baby picture that we can study and analyze to understand our cosmic origins. The universe is not just expanding and evolving, it's carrying forward information from its birth, encoded in the oldest light in existence. As scientists continue to study this primordial radiation with ever more sensitive instruments, they uncover new details about cosmic history. Each discovery adds another piece to our understanding of how the universe evolved from its hot, dense origins to the vast, complex cosmos we see today. The cosmic microwave background's silent memory continues to speak to those who know how to listen, revealing secrets of a time when the universe was less than 1,000th of its current age. The fact that we can detect and analyze this ancient light at all is a testament to human ingenuity and curiosity. From the accidental discovery by Penzias and Wilson to the precision measurements of modern space missions, our study of the CMB represents one of humanity's greatest scientific achievements. We have learned to read the subtle patterns in this primordial radiation, decoding a message that has crossed almost the entire observable universe to reach us. Tonight, as you gaze at the stars, remember that you're looking not just outward in space, but backward in time. And behind those stars, filling every direction of the sky, is an even older light, the faint afterglow of creation itself. The cosmic microwave background's silent memory surrounds us always, connecting us to our deepest cosmic origins and reminding us that we are part of a universe with a beginning, a history, and a still unfolding future. Long before there were stars, planets, or any of the cosmic structures we see today, there was a moment when light first began to move freely through the universe. This wasn't a sudden event like flipping on a light switch, but rather a gradual transition, cosmic dawn that would transform the very nature of the universe itself. To understand this pivotal moment, we must journey back to when the universe was approximately 380 years old. Before this time, the cosmos was an intensely hot, dense plasma soup of protons, electrons, and photons all interacting so frequently that light could barely travel before being scattered in a new direction. The universe was effectively opaque, like trying to see through thick fog where light bounces randomly between countless water droplets. In this primordial state, photon particles of light were trapped in a constant dance with matter. Each time a photon would begin its journey, it would almost immediately encounter a free electron and scatter, changing direction. This continuous scattering prevented light from traveling any significant distance. The universe was, in essence, a brilliant but impenetrable glow, with energy and matter in constant chaotic interaction. But as the universe expanded, it also cooled. Eventually, the temperature dropped to about 30 degrees Kelvin, still incredibly hot by human standards, but cool enough for something remarkable to happen. At this temperature, protons and electrons could finally combine to form neutral hydrogen atoms in a process scientists call recombination. This wasn't the first time such unions had been attempted. Earlier in cosmic history, any hydrogen atoms that formed were immediately torn apart by the intense radiation field. But now, the universe had cooled enough for these atoms to remain stable. This transformation from a plasma of charged particles to a gas of neutral atoms had a profound effect on light. Without free electrons to scatter them, photons could suddenly travel unimpeded across the universe. Light was liberated, free to move in straight lines for the first time. The universe, which had been opaque since its birth, suddenly became transparent. This moment of recombination created the cosmic microwave background radiation we discussed in the previous chapter. But it also marked the beginning of an entirely new phase in cosmic history, a time when light could travel vast distances, when it could, in a very real sense, meet itself. What does it mean for light to meet itself? Imagine the universe shortly after recombination. Photons that had been trapped in the hot plasma were suddenly released, traveling outward in all directions. Some of these photons moved in nearly parallel paths, separated perhaps by the vast distances that would later become galaxy clusters. As these photons traveled through the expanding universe, the invisible hand of gravity was slowly gathering matter into denser regions. These density fluctuations, the same ones imprinted in the cosmic microwave background, would eventually grow into the cosmic web of filaments, walls, and voids that characterize our universe today. As this structure began to form, it affected the paths of those ancient photons. Some were pulled slightly toward regions of greater density, their trajectories bent by the gravitational influence of concentrating matter. Others passed through relatively empty regions, continuing on more direct paths. Over millions and billions of years, these subtle differences in path could bring together photons that originated from nearly the same region of the early universe, but traveled along different routes. In a very literal sense, light that began its journey in the same cosmic neighborhood could meet itself after circling through the developing structure of the universe. This meeting wasn't just theoretical, it had profound implications for the evolution of the cosmos. As light moved through the universe, it interacted with the matter it encountered. Neutral hydrogen atoms could absorb certain wavelengths of light, becoming ionized in the process. When this happened, the freed electrons could then scatter other photons, creating a complex interplay between light and matter that would shape the future development of cosmic structure. The period after recombination is often called the Dark Ages of the universe. Not because there was no light, the cosmic microwave background was still bright by astronomical standards, but because there were no sources of new light. Stars had not yet formed, and the universe was filled with neutral hydrogen and helium, along with the ever fainter glow of the cosmic microwave background as it cooled through the expansion of space. During these cosmic dark ages, the meeting of the first light with the evolving matter fields was subtle but crucial. Photons from the cosmic microwave background interacted with the slightly denser regions of neutral hydrogen, depositing small amounts of energy that affected the temperature and ionization state of these gas clouds. This energy transfer, minute on local scales but significant when summed across the entire universe, influenced how quickly matter could collapse to form the first stars. The Dark Ages wouldn't last forever. As gravity continued to pull matter together, eventually the first stars began to form, probably around 100 million years after the Big Bang. These early stars were likely very different from the ones we see today, much more massive, hotter, and shorter-lived. They flooded their surroundings with intense ultraviolet radiation, beginning the process of reionizing the neutral hydrogen that had filled the universe since recombination. This era of reionization represents another crucial moment when light met the evolving universe. The ultraviolet photons from the first stars stripped electrons from hydrogen atoms, creating bubbles of ionized gas around each star or group of stars. These bubbles gradually expanded and merged, eventually reionizing most of the hydrogen in the universe by about 1 billion years after the Big Bang. During reionization, different populations of photons were interacting in complex ways. The ancient photons of the cosmic microwave background were still traveling through space, steadily cooling as the universe expanded. They were now joined by new photons from the first stars and galaxies, higher in energy and capable of ionizing the neutral hydrogen they encountered. The interaction between these different generations of light and the evolving matter fields shaped the universe we observe today. In regions where the first galaxies formed, intense star formation created the elements required for planets and eventually life. The light from these early stars not only ionized nearby hydrogen, but also began the process of chemical enrichment, as supernovae explosions scattered newly forged heavy elements into the intergalactic medium. These elements would later be incorporated into new generations of stars, some of which would host planets like our Earth. The meeting between the first light and itself wasn't just a single event, but an ongoing process that continues today. The cosmic microwave background photons still fill the universe, though they have cooled to just 2.7 degrees above absolute zero. They continue to interact with matter, providing a faint pressure and energy source that, while tiny, affects the development of the largest structures in the universe in measurable ways. Meanwhile, light from distant galaxies continues to journey across the cosmos, sometimes following paths that bring photons from the same source to our telescopes along different routes. This phenomenon, known as gravitational lensing, allows us to see multiple images of the same galaxy, each showing it at a slightly different moment in time. In a very real sense, we are observing light meeting itself after traveling for billions of years through the structured universe. The era when the first light met the evolving matter fields also established a pattern that would repeat throughout cosmic history. Light and matter exist in a perpetual dialogue, with radiation affecting the behavior of matter, and matter determining the paths and energies of radiation. This cosmic conversation has shaped the universe at every scale, from the largest superclusters of galaxies to the quantum fluctuations in the vacuum of space. The meeting of the first light with itself represents a kind of cosmic self-observation. The universe, through the interaction of its fundamental components, began to record information about its own structure. Patterns imprinted in the earliest light became part of the blueprint for future cosmic evolution. The universe was, in some sense, beginning to know itself through these interactions, creating a feedback loop between radiation and matter that would eventually lead to stars, planets, and life. This self-observation continues today on a much more literal level. The atoms in our bodies and the elements in our instruments were forged in stars that formed from gas that was influenced by the first light. When we build telescopes to detect the cosmic microwave background, we are creating a direct connection between the ancient photons that first moved freely through the universe and the conscious observers who evolved billions of years later. The universe, through us, is observing its own origins. The meeting of the first light with the evolving universe also established the fundamental timeline of cosmic history. Before recombination, the universe was dominated by radiation. Photons were so numerous and energetic that they determined the overall behavior of cosmic expansion. After recombination, as photons streamed freely through space, the universe transitioned to a matter-dominated era, with gravity gradually pulling material together to form the cosmic structures we see today. Much later, about 5 billion years ago, the universe entered a new phase dominated by dark energy, the mysterious force driving accelerated expansion. Throughout these transitions, the behavior of light, how it moved, how it interacted with matter, how its energy density compared to that of other componentures, been central to cosmic evolution. The first light meeting itself is also a profound metaphor for our own quest to understand the universe. When we study the cosmic microwave background, we are using light from the present, generated by our instruments and computers, to analyze light from the past, the ancient CMB photons. In this way, light from different eras meets to create knowledge, a pattern that repeats throughout human history, as each generation builds upon the discoveries of those who came before. As we look deeper into space with our telescopes, we are also looking further back in time. Eventually, we hope to directly observe the era of the first stars and the beginning of reionization. Already, the James Webb Space Telescope has begun to reveal galaxies from when the universe was less than 400 million years old. Each new observation pushes our vision closer to the moment when the universe first became transparent and light began its unimpeded journey across the cosmos. The meeting of the first light with itself marked the beginning of cosmic observation, the moment when the universe became, in a sense, observable to itself. Before this, information could not travel far. After it, information in the form of light could cross the cosmos, connecting distant regions and recording the evolving structure of space, time, and matter. This transmission of information is what makes scientific cosmology possible, allowing us to study the universe's history, composition, and fate. When Albert Einstein published his general theory of relativity in 1915, he forever changed our understanding of gravity. Rather than being a mysterious force that acts across distances, Einstein revealed that gravity is actually the curvature of space-time itself, created by the presence of mass and energy. This revolutionary insight led to one of the most remarkable predictions in the history of physics. Light, which has no mass, would nevertheless follow the curved paths of space-time, bending around massive objects. This prediction seemed so extraordinary that testing it became one of the first major challenges for Einstein's new theory. In 1919, during a total solar eclipse, the British astronomer Arthur Eddington measured the positions of stars that appeared near the edge of the Sun. He found that their positions were slightly shifted compared to their known locations, exactly as Einstein had predicted. Light from these distant stars was indeed bending as it passed through the curved space-time near our Sun. This confirmation of gravitational light deflection was merely the beginning. Einstein went further, suggesting that under the right circumstances, massive objects could act as cosmic lenses, focusing light like a glass lens focuses the image in a telescope. He calculated that if a distant star were perfectly aligned with a closer star and an observer on Earth, the light from the distant star would be magnified and appear as a perfect ring around the closest star, what we now call an Einstein ring. For decades, this prediction remained a theoretical curiosity. The chances of such perfect alignment seemed too small, and the technology to detect such subtle effects didn't exist. But as telescopes improved and our understanding of the universe expanded, astronomers began to realize that gravitational lensing wasn't just possible, it was happening all around us, on cosmic scales far grander than Einstein had imagined. The first gravitational lens was discovered in 1979, when astronomers noticed what appeared to be two identical quasars, extraordinarily bright galaxy cores, powered by supermassive black holes, positioned suspiciously close to each other in the sky. Further observations revealed the truth. There was only one quasar, but its light was being split into two images by a massive galaxy positioned between it and Earth. The galaxy's enormous mass had bent space-time enough to create multiple paths for the quasar's light to reach us, effectively letting us see the same object from two different angles simultaneously. This discovery opened a new window into the cosmos. Gravitational lensing allows us to see things that would otherwise be invisible, to look around cosmic corners, and to study the distribution of matter, including dark matter, throughout the universe. The phenomenon comes in several flavors, each revealing different aspects of cosmic structure. Strong lensing occurs when a massive object, like a galaxy cluster, creates multiple distinct images of background objects, or distorts them into spectacular arcs and rings. Weak lensing produces more subtle distortions that can only be detected statistically by analyzing the shapes of thousands of background galaxies. Microlensing happens when a smaller object, like an individual star or planet, temporarily brightens a background star as it passes in front of it. Perhaps the most visually stunning examples of gravitational lensing come from massive galaxy clusters. These enormous collections of hundreds or thousands of galaxies contain enough mass to severely warp the space-time around them. When light from more distant galaxies passes through this warped region, it follows curved paths, sometimes creating spectacular arcs of light that partially or completely encircle the cluster. These gravitational arcs aren't just beautiful, they're extraordinarily useful. By studying their precise shapes and arrangements, astronomers can map the distribution of matter within the lensing cluster, including the invisible dark matter that makes up about 85% of the cluster's mass. This gives us a way to see dark matter indirectly by observing its gravitational effects on light from more distant sources. Even more remarkably, these massive cosmic lenses can magnify distant objects that would otherwise be too faint to observe. The curved space-time around galaxy clusters can amplify the light from background galaxies by factors of 10, 20, or even more, effectively turning these clusters into natural cosmic telescopes. By looking through these gravitational telescopes, astronomers have been able to study galaxies from when the universe was less than 1 billion years old, galaxies so distant and faint that they would be invisible without the boost provided by gravitational lensing. This magnification effect allows us to study details of the early universe that would otherwise remain hidden. Distant galaxies that appear as mere smudges in direct observations can be resolved into star-forming regions and structural features when viewed through the magnifying lens of a massive cluster. In this way, gravitational lensing gives us a preview of what we might see with future, more powerful telescopes. But gravitational lensing doesn't just magnify distant objects, it can also create multiple images of the same source. When a massive object lies almost perfectly between Earth and a distant light source, the light can follow different paths around the lens. reaching us from different angles. This can create 2, 4, or even more images of the same object, arranged in patterns that depend on the exact distribution of mass in the lensing object. These multiple images represent the light from the same source arriving at Earth, along different paths through the curved spacetime around the lens. Because these paths have different lengths, the light from each image has been traveling for a slightly different amount of time. This means that if the source varies in brightness, as many cosmic objects Dao might see these variations happen at different times in each image. This time delay between lensed images provides a unique tool for measuring the expansion rate of the universe. By carefully timing how long it takes for a brightness change to appear in each image, astronomers can calculate the difference in path length, which in turn depends on the distances involved and the overall geometry of the universe. This technique has become one of the most precise methods for measuring the Hubble constant, which describes how quickly the universe is expanding. Gravitational lensing also allows us to see behind objects that would otherwise block our view. When light bends around a massive object, it can bring into view regions of space that would normally be hidden behind the lens. It's as if we're peeking around a cosmic corner, seeing parts of the universe that would otherwise be obstructed from our line of sight. This ability to see around cosmic corners has revealed otherwise hidden galaxies, distant supernovae, and even entire clusters that lie behind closer, massive objects. In this way, gravitational lensing expands our cosmic field of view, allowing us to observe a more complete picture of the universe than would be possible with direct observation alone. Perhaps the most profound aspect of gravitational lensing is that it shows us the universe from multiple perspectives simultaneously. When we observe a quadruply lensed quasar, we're seeing the same object from 4 different angles at once. These different lines of sight can reveal variations in the structure of the quasar and its surrounding environment that would be impossible to detect from our single vantage point on Earth. This multi-perspective view is particularly valuable for studying objects that change over time. A supernova that appears in one lensed image will eventually appear in the others, allowing astronomers to predict when and where these cosmic explosions will become visible. By preparing in advance, they can capture the earliest moments of these stellar deaths, gathering crucial data about the explosion mechanics that would otherwise be missed. Gravitational lensing also reveals the 3-dimensional structure of the cosmic web, the vast network of filaments, walls, and voids that forms the large-scale architecture of the universe. As light travels through this cosmic web, it encounters varying concentrations of matter that bend its path in subtle ways. By analyzing the slight distortions in the shapes of millions of distant galaxies, astronomers can reconstruct the distribution of matter along the line of sight, creating a 3-dimensional map of both visible and dark matter throughout cosmic history. This mapping of the cosmic web through weak gravitational lensing has become one of our most powerful tools for understanding how structure forms and evolves in the universe. It reveals how dark matter forms the skeleton upon which galaxies and galaxy clusters are built, and how the mysterious dark energy affects the growth of these structures over time. On smaller scales, gravitational microlensing allows us to detect objects that emit little or no light of their own. When a star, brown dwarf, or planet passes almost directly between Earth and a more distant star, it can temporarily magnify the background star's light. By carefully analyzing these brightening events, astronomers can determine the mass and other properties of the lensing object, even if it's too faint to be seen directly. This technique has led to the discovery of numerous planets orbiting stars other than our Sun, including some that orbit at distances where liquid water might exist on their surfaces. It has also helped us understand the population of small, faint stars and stellar remnants that would otherwise remain invisible, giving us a more complete census of our galaxy's contents. The future of gravitational lensing observations looks even more promising. As telescopes become more powerful and survey more of the sky at higher resolution, the number of known gravitational lenses is expected to increase from hundreds to thousands or even tens of thousands. Each of these cosmic lenses will provide another window into the structure and evolution of the universe. Space-based missions dedicated to measuring weak lensing across the entire sky will create the most detailed maps yet of the distribution of dark matter throughout cosmic history. These maps will reveal how cosmic structure has evolved under the competing influences of gravity, which pulls matter together, and dark energy, which drives the accelerating expansion of the universe. Advanced computer algorithms are also enhancing our ability to extract information from lensed images. Techniques like gravitational lens modeling can reconstruct both the mass distribution in the lensing object and the true appearance of the lensed source, effectively undoing the distortions caused by the lens to reveal the original image. Perhaps most excitingly, gravitational lensing may help us detect some of the very first stars and galaxies that formed after the Big Bang. The combination of natural gravitational telescopes like massive galaxy clusters with our most advanced space observatories could reveal objects from when the universe was just a few 100 million years old, the dawn of cosmic structure, formation. As our understanding and observation of gravitational lensing continues to advance, we gain an increasingly complete picture of our universe from multiple angles simultaneously. We see around cosmic corners, observe objects that would otherwise be too faint to detect, map invisible dark matter, and piece together the three-dimensional structure of the cosmic web throughout its evolution. Einstein's prediction of light bending through curved space-time has evolved from a theoretical curiosity to one of our most powerful tools for cosmic exploration. Through the gravitational lensing effect, we have learned to use the universe's own structure as a vast array of natural telescopes, allowing us to see farther, clearer, and more comprehensively than would otherwise be possible. In many ways, gravitational lensing represents the universe observing itself. The light from distant objects is shaped and guided by the very structure of the cosmos, creating multiple perspectives and revealing hidden connections. As you drift towards sleep tonight, consider this remarkable fact. The universe doesn't just contain the objects we see, it actively shapes how we see them, bending light around massive objects to create a richer, more complete picture of reality than any single line of sight could provide. What we call empty space is anything but empty. Between galaxies, between stars, between atoms, and even within the atoms themselves exists what physicists refer to as the quantum vacuum, a state that appears devoid of matter yet teems with invisible activity. This seeming emptiness is actually a roiling sea of quantum fields, where particles and antiparticles briefly flicker into existence before annihilating each other and disappearing back into the vacuum from which they emerged. These ephemeral particles, called virtual particles, aren't just theoretical constructs, they have measurable effects on the physical world. They push apart closely spaced metal plates in the Casimir effect, alter the magnetic properties of electrons, and even cause black holes to radiate energy through Hawking radiation. The vacuum of space, it turns out, keeps a record. It remembers what has happened within it and around it, preserving traces of past interactions in subtle quantum echoes. Imagine dropping a pebble into a perfectly still pond. Ripples spread outward, gradually diminishing in strength, but continuing their journey across the water's surface. In somewhat similar fashion, every event in the universe-every interaction between particles, every exchange of energy creates ripples in the quantum fields that permeate all of space. These ripples don't simply vanish, they propagate outward, interacting with other ripples, sometimes reinforcing, sometimes cancelling, but always carrying information about their origins. This phenomenon becomes particularly evident in what physicists call the quantum vacuum fluctuations, random variations in the energy of those temporary virtual particles that pop in and out of existence. These fluctuations aren't truly random in the sense of being completely unpredictable or patternless. Instead, they carry the imprints of past events, preserving quantum echoes of interactions that happened long ago. One of the most striking examples of how the vacuum remembers past events comes from the Casimir effect. When two uncharged metal plates are placed extremely close together in a vacuum, they experience a small but measurable attractive force. This force arises because only certain wavelengths of virtual particles can exist in the narrow gap between the plates, while a wider range of virtual particles pushes from the outside. The end result is that the vacuum itself seems to generate a force, pushing the plates together. What's fascinating about this effect is that it demonstrates how the vacuum responds differently depending on the boundary conditions imposed upon it. The presence of the metal plates alters the quantum field, creating a new pattern of vacuum fluctuations that remembers and reflects the geometry of its surroundings. The vacuum has, in essence, recorded the presence of the plates and responded accordingly. This responsiveness of the vacuum extends far beyond laboratory experiments. Throughout the cosmos, Vacuum fluctuations preserve traces of past interactions between matter, energy, and the fields themselves. When a star explodes as a supernova, sending a shock wave of particles and radiation outward, it doesn't just affect the visible matter it encounters, it also imprints itself on the quantum vacuum, creating patterns in the virtual particles that continue long after the initial explosion has faded. These quantum echoes become particularly significant near objects with strong gravitational fields, like black holes. Near a black hole's event horizon, the boundary, beyond which nothing can escape, the vacuum becomes highly distorted. Virtual particle pairs that would normally appear and disappear together can be separated if one falls into the black hole while the other escapes. The escaping particles form Hawking radiation, named after the physicist Stephen Hawking, who first predicted this phenomenon. What's remarkable about Hawking radiation is that it carries information about the black hole that created it: its mass, its angular momentum, its electric charge. The quantum vacuum near the black hole records these properties and reflects them back to the universe through the radiation it emits. Even as the black hole itself keeps its secrets locked behind the event horizon, the vacuum surrounding it whispers those secrets to the cosmos through subtle quantum patterns. But the quantum vacuum doesn't just record the present state of things, it preserves echoes from the past as well. According to some theoretical models, the vacuum might retain imprints of events that happened billions of years ago, potentially including remnants from the earliest moments after the Big Bang. These quantum echoes could provide a unique window into cosmic history, complementing the information we get from more familiar sources like the cosmic microwave background radiation. One intriguing possibility is that the quantum vacuum might preserve traces of phase transitions in the early universe moments, when the fundamental forces of nature separated from each other as the cosmos cooled. These transitions may have created subtle patterns in the vacuum that persist to this day, like fossils embedded in cosmic bedrock, waiting for sufficiently sensitive instruments to detect them. The vacuum's memory extends to the realm of quantum entanglement as well. When particles become entangled, their properties become correlated in ways that defy classical physics, no matter how far apart they may later travel. This spooky action at a distance, as Einstein famously described it, suggests that space itself remembers the connections between particles, preserving their relationship across vast distances and timescales. Recent experiments have shown that entanglement can be swapped and transferred between particles that have never directly interacted with each other. This implies that the quantum vacuum serves as a kind of medium or repository for these entangled states, maintaining their correlations even as the physical particles move apart. The vacuum becomes a record keeper of quantum relationships, preserving the subtle connections that bind the cosmos together at its most fundamental level. The quantum vacuum may even record traces of objects that passed through it long ago. When a charged particle moves through space, it distorts the electromagnetic field around it. These distortions don't simply disappear when the particle moves on, they propagate outward as electromagnetic waves, carrying information about the particle's charge, velocity, and trajectory. In this way, the vacuum retains an echo of the particle's passage, a subtle memory written in fields rather than matter. These vacuum memories become especially significant when we consider the possibility of cosmic string hypothetical one-dimensional defects in the fabric of space-time that may have formed during phase transitions in the early universe. If they exist, cosmic strings would leave distinctive signatures in the quantum vacuum, traces that might be detectable through their gravitational effects or their influence on passing light rays. The quantum vacuum doesn't just passively record these echoes, it actively processes and transforms them through ongoing interactions between virtual particles and fields. Information stored in vacuum fluctuations can be transferred, modified, and even amplified through a variety of quantum mechanisms, creating a dynamic network of echoes that evolves over time. This processing capacity of the vacuum becomes evident in the phenomenon known as vacuum birefringence. When light passes through a region of space with an extremely strong magnetic field, the vacuum itself becomes slightly anisotropicate, affects different polarizations of light differently, effectively splitting the light into two components that travel at slightly different speeds. This effect, predicted by quantum electrodynamics, has been observed near neutron stars with powerful magnetic fields. What's remarkable about vacuum birefringence is that it shows how the vacuum can be temporarily changed by external conditions, developing properties it wouldn't normally possess. The vacuum remembers the presence of the magnetic field and alters its behavior accordingly, becoming a different kind of medium for as long as the field persists. These quantum echoes in the vacuum may have played a crucial role in the evolution of the universe. During the inflationary epoch period of exponential expansion, thought to have occurred in the first fraction of a second after the Big Bang, quantum fluctuations in the vacuum were stretched to cosmic scales, becoming the seeds for all the structure we see in the universe today. What began as tiny ripples in quantum fields became the galaxies, clusters, and superclusters that form the cosmic web. In this sense, the large-scale structure of the universe itself is a vast amplification of quantum echoes, a macroscopic manifestation of patterns that began at the smallest possible scales. The vacuum didn't just record these early fluctuations, it preserved them through inflation and allowed them to grow into the cosmic architecture that surrounds us today. The quantum vacuum may also preserve echoes of events that haven't happened yet, at least not from our perspective. According to some interpretations of quantum mechanics, particularly those involving retrocausality or advanced waves, the vacuum might contain information flowing backward in time, creating echoes of future events that influence the present. While highly speculative, such ideas highlight the complex relationship between the quantum vacuum, information, and the flow of time. Even more intriguing are the potential connections between vacuum fluctuations and dark energy, the mysterious force driving the accelerating expansion of the universe. One explanation for dark energy suggests that it might be related to the energy inherent in vacuum fluctuations themselves. If this connection proves correct, then the quantum echoes preserved in empty space might hold the key to understanding one of the greatest cosmic mysteries of our time. The vacuum's capacity to record and preserve information also raises profound questions about the ultimate fate of the universe. As the cosmos continues to expand and cool, stars will gradually burn out, black holes will evaporate through Hawking radiation, and matter as we know it will disperse into an increasingly diffuse state. But even in this remote future, the quantum vacuum will remain, potentially preserving echoes of the once vibrant universe that existed before. These eternal quantum echoes might represent the final legacy of our cosmosubtle patterns of fluctuations that carry, in highly encoded form, the history of everything that ever happened. Like whispers in an empty cathedral, these faint remnants could persist long after all other traces have faded, a quantum memorial to a universe that once teemed with stars and life. The study of these quantum echoes in empty space is still in its infancy. Many of the effects are extraordinarily subtle, requiring incredibly sensitive instruments or extreme conditions to detect. But advances in quantum optics, high-precision interferometry, and space-based gravitational wave detectors are gradually opening new windows into this hidden realm of vacuum physics. Experiments like LIGO, Laser Interferometer, Gravitational Wave Observatory, have demonstrated our growing ability to detect incredibly faint ripples in space-time itself, gravitational waves that stretch and compress space by less than the width of a proton. These same technologies, refined and enhanced, might someday allow us to detect the even subtler quantum echoes preserved in the vacuum. Future experiments might include searching for vacuum fluctuations that carry imprints of the early universe, looking for evidence of cosmic strings through their effects on the quantum vacuum, or detecting the subtle anisotropies in empty space created by powerful cosmic events. Each discovery would add another piece to our understanding of how the vacuum records and preserves information. The quantum echoes in empty space remind us that emptiness, in the quantum world, is an illusion. What appears to be nothing is actually a complex, dynamic system of fields and virtual particles, constantly fluctuating according to the laws of quantum mechanics. These fluctuations aren't just random noise, they're a repository of information, a cosmic memory bank that preserves traces of events across space and time. As you drift towards sleep tonight, consider the seemingly empty space around you. Between the atoms of air, between the molecules of matter, within the very structure of space itself, quantum fields are fluctuating, virtual particles are appearing and disappearing, and subtle patterns are forming and dissolving. This quantum dance isn't just happening, no, it carries echoes from the distant past and seeds for the future, connecting your present moment to the vast expanse of cosmic history. The quantum vacuum, with its capacity to record and preserve information, offers a profound metaphor for the interconnectedness of all things. Nothing truly happens in isolation. Every event leaves its mark on the fields that permeate all of space, creating ripples that travel outward and interact with other ripples in an endless conversation of energy and information. The universe remembers, and its memory lives in the quantum echoes that fill even the emptiest reaches of space. At the dawn of the 20th century, physics underwent a revolution. The solid, deterministic world of classical physics gave way to the strange, probabilistic realm of quantum mechanics. Among the many mind-bending concepts that emerged was the observer effect, the idea that the very act of measurement can influence what is being measured. This principle, demonstrated in countless laboratory experiments, raises profound questions when we extend it to cosmic scales. Does observation affect reality at the level of the universe itself? Could the cosmos, in some sense, be aware of being observed? The observer effect in quantum mechanics challenges our intuitive understanding of reality. In the famous double-slit experiment, particles like electrons behave differently depending on whether they are being watched. When unobserved, they travel as waves, passing through both slits simultaneously and creating an interference pattern. But when observed, they behave like discrete particles, passing through just one slit or the other. The mere act of observation appears to collapse a wave of possibilities into a single, definite outcome. This peculiar behavior has been confirmed repeatedly in increasingly sophisticated experiments. Quantum particles seem to exist in states of probability superpositions of multiple possible states until the moment of observation, when they decide on a single state. This phenomenon, known as wave function collapse, has been interpreted in various ways, from the Copenhagen interpretation's emphasis on measurement to the many worlds interpretation's suggestion that all possibilities occur in branching realities. But what happens when we step back and consider the implications for the universe as a whole? Is the cosmos itself subject to something like the observer effect? Does the universe evolve differently depending on whether and how it is observed? These questions take us into speculative territory at the intersection of physics, philosophy, and cosmology. Unlike the controlled environment of a laboratory experiment, the universe presents unique challenges for thinking about observation and measurement. For one thing, the universe as a whole has no external observer. Any observation happens from within the system being observed. For another, quantum effects typically become negligible at macroscopic scales, making it unclear whether quantum principles like the observer effect apply to cosmic structures. Nevertheless, several theoretical frameworks suggest that observation might indeed play a role in cosmic evolution. One approach comes from quantum cosmology, which attempts to apply quantum mechanics to the universe as a whole. In this view, the universe might exist in a superposition of different possible states, with our observations selecting or emphasizing particular realizations from this cosmic wave function. The anthropic principle offers another perspective. In its weak form, this principle simply notes that our observations of the universe are constrained by the requirements for our existence. We can only observe universes, or regions of a universe, that allow observers like us to evolve. In its stronger forms, the anthropic principle suggests that the universe must have properties that allow observation to occur, implying a kind of selection effect, where observation itself becomes relevant to cosmic reality. These ideas become especially intriguing in the context of the multiverse hypothesis. If our universe is just one of many in a vast multiverse, perhaps with different physical laws and constants, then the observer effect might operate as a selection mechanism. We necessarily find ourselves in a universe that can be observed because observation itself requires certain conditions. The act of observation selects from the possibilities those universes where observers can exist. But the relationship between observation and cosmic reality might be even more fundamental. Some interpretations of quantum mechanics, such as the participatory anthropic principle proposed by physicist John Wheeler, suggest that the universe requires conscious observers to fully realize its existence. Wheeler famously described this as a self-excited circuit, where observers emerge from the universe and then, through their observations, give reality to the universe from which they emerged. This view doesn't suggest that human consciousness specifically is necessary for the universe only, that some form of observation or information processing is required for the universe to transition from multiple potentialities, specific actualities. Such observation could conceivably come from any sufficiently complex system capable of registering and processing information about its environment. In Wheeler's memorable phrase, "The universe is a self-excited circuit. From a strange beginning, the universe bootstraps itself into a more concrete existence. The cosmos not only produces observers but needs them to fully realize itself through the conversion of possibilities into actualities via the act of observation." Of course, these ideas shouldn't be misconstrued to suggest that human consciousness somehow creates the physical universe. The cosmos existed for billions of years before humans evolved, and will likely continue long after our species is gone. Stars formed, galaxies collided, and planets orbited even with no human observer to witness them. The universe clearly evolves according to physical laws independent of human perception. Yet at the quantum level, the role of observation becomes more ambiguous. Quantum systems do behave differently when measured versus when left undisturbed. And since the entire universe presumably began in a quantum state during the earliest moments after the Big Bang, perhaps some version of the observer effect operated even then, with quantum fluctuations being observed or measured, not by conscious beings, but by their interaction with other parts of the emerging universe. This perspective aligns with the concept of decoherence in quantum mechanics, the idea that quantum systems lose their wave-like properties through interactions with their environment. The environment effectively measures the quantum system continuously, causing it to behave more like classical, definite objects. In the early universe, decoherence would have played a crucial role in the transition from quantum fluctuations to the large-scale structure we observe today. Perhaps the most profound connection between observation and cosmic evolution lies in how information flows through the universe. Information, in the physics sense, relates to the distinction between different possible states of a system. When we observe something, we acquire information about which of many possible states has been realized. This information processing happens not just in human brains, but in any system that registers and responds to its environment, from single-celled organisms to stars sensing the gravitational pull of their neighbors. From this perspective, the universe is constantly observing itself through countless interactions between its components. Each atom that absorbs a photon, each molecule that changes conformation in response to temperature, each black hole that warps space-time around it all, these represent information exchanges, a kind of observation happening continuously throughout the cosmos. This universal self-observation creates a network of information flow that shapes cosmic evolution. The patterns we observe in galaxies, the distribution of matter across the cosmos, the emergence of complex systems like living organisms reflect how information has propagated and been processed through cosmic history. The universe doesn't just contain information, it processes and transforms it through ongoing interactions between its parts. Some philosophers and scientists have suggested that this information processing capacity might represent a kind of proto-consciousness distributed throughout the cosmos. While very different from human consciousness, this perspective sees awareness not as something unique to brains, but as a fundamental aspect of information processing that exists in varying degrees throughout nature. Physicist Freeman Dyson expressed this view when he wrote, "Mind is already inherent in every electron, and the processes of human consciousness differ only in degree, but not in kind, from the processes of choice between quantum states, which we call chance, when they are made by electrons." This spectrum of awareness, from the rudimentary information processing of particles to the complex consciousness of living beings, suggests a universe that doesn't merely exist, but experiences its own existence to varying degrees through its myriad components. The cosmos observes itself not only through human eyes, but through countless interactions between its elements, each registering and responding to aspects of reality in its own way. The growing field of integrated information theory, IIT, offers one framework for thinking about this spectrum of awareness. According to IIT, consciousness correlates with a system's capacity to integrate information in complex ways. Systems with higher levels of integrated information, like human brains, possess correspondingly higher levels of consciousness. But even simple systems might possess minimal forms of experience proportional to their information integration capabilities. If we apply this thinking to cosmic scales, we might speculate about forms of consciousness that transcend individual organisms or even planets and stars. perhaps galaxy clusters, through the gravitational and electromagnetic interactions between their components, integrate information in ways that constitute a form of experience utterly unlike anything we can imagine. The cosmic web itself might represent an information processing system of unimaginable complexity, integrating signals that travel across billions of light-years of space. These speculations take us far beyond conventional science into philosophical territory. Yet they remind us that observation isn't merely a passive recording of pre-existing facts, it's an active process that participates in the unfolding of reality. When we observe distant galaxies through our telescopes, we aren't just witnessing remote cosmic events, we're creating connections across space and time, integrating those distant objects into our sphere of awareness, and, perhaps in some subtle way, influencing how reality manifests. The observer effect in quantum mechanics, then, might be a specific instance of a more general principle, that reality emerges through the interaction between systems that register information about each other. The universe doesn't just exist, it exists in particular ways because of how its components observe and respond to each other. Consciousness, human or otherwise, represents an especially complex and integrated form of this universal information processing. This perspective offers a middle path between two extreme views: the idea that human consciousness somehow creates reality, a solipsistic view that most scientists reject, and the view that consciousness is merely an epiphenomenon with no significant role in cosmic evolution. Instead, consciousness might be understood as one expression of the universe's inherent capacity to observe its special in its complexity and self-reflection, but continuous with information processing happening throughout nature. The potential links between consciousness and cosmology extend beyond the observer effect. Some scientists have noted striking parallels between the structure of the cosmic web, the vast network of galaxy filaments and voids that forms the large-scale architecture of the universe, and the neural networks of brains. Both exhibit complex, hierarchical organization, optimized for information flow. Both balance integration and differentiation, creating structures that process information at multiple scales simultaneously. These parallels don't prove that the universe is conscious in any human-like sense, but they suggest that the principles governing the organization of conscious systems might be reflected in cosmic structure as well. Perhaps the universe organizes itself according to patterns that naturally emerge when information flows through complex networks, whether at the scale of neurons or galaxies. The universe's apparent fine-tuning for complexity offers another intriguing connection. Many physical constants and laws seem precisely calibrated to allow for the emergence of complex structures like stars, planets, and eventually life. A slight change in these values would create universes dominated by either uniform gas or black holes, with no possibility for the diverse, information-rich systems we observe. This fine-tuning has been explained in various ways, from the anthropic principle and multiverse theories to arguments for intelligent design. But another perspective sees it as reflecting a cosmos naturally oriented toward increasing complexity and information processing. In this view, universes that can observe themselves through the emergence of complex structures, capable of registering and integrating information, represent a natural evolutionary development in a multiverse where different configurations are constantly being explored. The concept of a universe evolving toward greater complexity and self-observation aligns with recent thinking about the role of information in physics. Some theorists suggest that information, rather than matter or energy, might be the most fundamental aspect of reality. In this it-from-bit perspective, proposed by John Wheeler, the physical universe emerges from information and the distinctions between different possible states. If information is indeed fundamental, then the cosmos doesn't just happen to produce observer-observation itself, becomes central to how reality manifests. The universe evolves, not only according to equations of motion, but through an ongoing process of information exchange that gradually realizes specific patterns from a vast landscape of possibilities. This information-centric view offers a new perspective on consciousness as well. Rather than being an anomalous product of complex brains, consciousness might represent an especially integrated form of the information processing that happens throughout nature. Our awareness would be not separate from cosmic processes, but a particularly vivid expression of the universe's inherent capacity to observe itself. Such perspectives blur the traditional boundaries between observer and observed, between consciousness and cosmos. They suggest a universe that doesn't merely contain conscious beings, but that manifests different forms and degrees of awareness throughout its structure, from the rudimentary information registration of particles to the integrated experience of living organisms to possibly larger-scale patterns of information flow in cosmic structures. As we contemplate these connections between consciousness and cosmology, we should maintain scientific humility. Many of these ideas remain speculative, pushing the boundaries of our understanding in both physics and the science of consciousness. Yet they offer a compelling vision of a universe that doesn't just exist, but experiences its own existence through myriad forms of observation and information processing. Perhaps the most profound implication is that human consciousness, rather than standing apart from cosmic processes, represents one expression of the universe's capacity to observe itself. When we gaze at the stars, the universe is, in a very real sense, looking at itself through human eyes, creating a loop of observation where the cosmos produces beings capable of witnessing and understanding the very processes that created them. As you drift towards sleep tonight, consider this remarkable possibility. Your consciousness, with its capacity to observe and reflect, might be not just a product of cosmic evolution, but a participant in how the universe realizes itself. Through your awareness, the cosmos experiences a unique perspective on its own existence, adding another layer to the vast network of observation that spans from quantum particles to galactic superclusters. In this way, every conscious moment represents a collaboration between observer and cosmos, a point where the universe looks back at itself and, perhaps, comes to know itself a little more completely. At the heart of our understanding of the physical universe lies a profound and beautiful concept: symmetry, far more than just a pleasing visual arrangement. Symmetry in physics refers to the deep invariances that underlie the laws of nature, the ways in which certain aspects of reality remain unchanged when viewed from different perspectives or under different transformations. These symmetries serve as a hidden architecture of the cosmos, revealing connections between seemingly unrelated phenomena and pointing toward the fundamental unity beneath diverse appearances. The laws of physics exhibit remarkable symmetry across both space and time, move from one location to another, and the same physical principles apply. Wait an hour, a day, or a century, and gravity still pulls objects toward each other with the same mathematical precision. Rotate your perspective, and the laws governing particle interactions remain consistent. These basic symmetries, translational, temporal, and rotational, seem almost obvious to us, yet they encode profound truths about the universe's consistency and predictability. Even more fascinating are the subtle symmetries discovered in the 20th century. One such symmetry is parity, or mirror reflection. For most physical processes, performing an experiment and viewing its mirror image would yield equivalent results. The laws governing electromagnetic interactions, for instance, don't distinguish between left and right. They work exactly the same in a mirror world as they do in our own. But nature holds surprises. In 1956, physicists Chen-Ning Yang and Sungdao Li proposed that weak nuclear interactions, none of the four fundamental forces, might actually violate parity symmetry. Experiments confirmed this stunning prediction, showing that the weak force behaves differently in a mirror-reflected world. Suddenly, the universe revealed an intrinsic handedness, a preference for leftover right, or vice versa, in certain interactions, challenging the assumption that all laws of physics must be perfectly symmetric. This discovery set physicists on a quest to find a more comprehensive symmetry that could restore the elegant mathematical harmony they sought. They found that by combining parity, P, with charge conjugation, C, which transforms particles into their antiparticles, they could formulate a new symmetry called CP. For a while, it seemed that even though parity alone was violated, the combined operation of switching left with right and matter with antimatter would preserve symmetry in all interactions. But nature had another surprise in store. In 1964, James Cronin and Val Fitch discovered that CP symmetry is also violated, though very subtly, in certain rare interactions involving subatomic particles called kaons. Even the combined transformation of mirror reflection and matter-antimatter exchange wasn't enough to fully restore the symmetry of physical law. This led to the current understanding that the most fundamental symmetry appears to be CPT, the combination of charge conjugation, parity, and time reversal. According to present theories, if you take any physical process, reverse the charges of all particles involved, reflect it in a mirror, and run it backward in time, the result must obey exactly the same laws as the original process. CPT symmetry stands as one of the most profound and theoretically robust symmetries in modern physics. These symmetries and their occasional violations serve as cosmic mirrors, reflecting the deep structure of reality and revealing how the universe observes its own behavior through the patterns of its physical laws. When a symmetry is perfect, it tells us that certain distinctions are irrelevant to how the universe operates. When a symmetry is broken or violated, it highlights meaningful differences that shape cosmic evolution in specific directions. Perhaps the most powerful illustration of symmetry's role in physics comes from Emmy Noether's groundbreaking theorem, which established a fundamental connection between symmetries and conservation laws. Noether proved that for every continuous symmetry in physics, there exists a corresponding quantity that is conserved unchanged over time. Translational symmetry in space leads to conservation of momentum. Rotational symmetry leads to conservation of angular momentum. Symmetry in time leads to conservation of energy. These conservation laws aren't arbitrary rules imposed on the universe. They emerge naturally from the symmetric structure of physical reality. The universe preserves certain quantities not because of some external mandate, but because its own mathematical architecture requires it. In this way, the cosmos observes its own symmetries through the invariant quantities that persist amid constant change. Antimatter represents another profound symmetry in the cosmos, a mirror image of ordinary matter with opposite charge but identical mass. For every type of particle, there exists a corresponding antiparticle. Electrons have positrons, protons have antiprotons, and so on. When matter and antimatter meet, they annihilate each other in a burst of pure energy, transforming mass back into radiation. This matter-antimatter symmetry raises one of the greatest mysteries in modern cosmology. Why does our universe contain so much more matter than antimatter? According to our best theories of the early universe, matter and antimatter should have been created in equal amounts after the Big Bang. That would have led to complete annihilation, leaving a cosmos filled with radiation but no matter to form stars, planets, or life. The slight asymmetry that allowed matter to dominate is estimated at just one extra particle of matter per billion particle-antiparticle pairs remains a profound puzzle, suggesting either undiscovered physics or a fundamental aspect of reality that slightly favors matter over antimatter. Time reversal provides yet another cosmic mirror through which the universe might observe itself. Most fundamental laws of physics work equally well running forward or backward in time. Maxwell's equations for electromagnetism, Einstein's equations for gravity, and Schrödinger's equation for quantum mechanics all remain valid if the direction of time is reversed. In theory, these physical processes are reversible, with no inherent arrow distinguishing past from future. Yet our lived experience tells a different story. We remember the past but not the future. Coffee cools rather than spontaneously heating up. Broken eggs don't reassemble themselves. The universe expands rather than contracts. This apparent contradiction between time-symmetric laws and time-asymmetric experience constitutes the arrow of time, problema fundamental mystery in physics. The resolution seems to lie in statistical behavior rather than fundamental law. When many particles interact, the system tends to evolve from less probable to more probable states from order to disorder. This statistical tendency, formalized in the second law of thermodynamics as increasing entropy, creates the time asymmetry we experience, even though the underlying laws remain symmetric. The arrow of time emerges not from the basic equations, but from the boundary conditions of the universe specifically, the extraordinarily low entropy state in which the cosmos began. This cosmic memory of initial conditions, preserved in the flow of entropy, represents another way the universe observes its own history. The direction of time itself becomes a record of the universe's evolution from its highly ordered beginning toward increasing disorder, creating an asymmetry that shapes every physical process we experience. Symmetry extends beyond individual laws to the very fabric of space-time. According to Einstein's general relativity, space and time form a unified four-dimensional continuum that curves in response to matter and energy. The equations describing this relationship exhibit a profound symmetry known as general covariance. They maintain the same form regardless of the coordinate system used to express them. This symmetry reflects the profound insight that the laws of physics should not depend on the arbitrary ways we choose to label points in spacetime. At the quantum level, additional symmetries emerge. Quantum field theory, our most comprehensive framework for understanding particle physics, reveals symmetries that relate different forces and particles to each other. The standard model of particle physics incorporates several gauge symmetries that determine how fundamental forces operate and particles interact. These symmetries aren't just mathematical conveniences. They represent deep principles that the universe appears to follow at its most fundamental level. Some of these symmetries can be broken under certain conditions, leading to profound physical consequences. In the earliest moments after the Big Bang, the universe was in a state of such extreme energy that the electromagnetic and weak nuclear forces were unified as a single electroweak force. As the cosmos expanded and cooled, this symmetry broke, separating the two forces and giving rise to the distinct physical behaviors we observe today. This phenomenon, known as spontaneous symmetry breaking, shows how the universe can transition from more symmetric to less symmetric states, while still preserving the underlying symmetry in its fundamental equations. The cosmos may also encode symmetries at scales we're only beginning to explore. String theory, a candidate for unifying quantum mechanics and general relativity, suggests additional symmetries involving extra dimensions of space curled up at submicroscopic scales. These hidden symmetries might explain the apparent arbitrariness of certain physical constants and provide a framework for understanding the fundamental forces as manifestations of a single, unified interaction. Through all these symmetries preserved, broken, hidden, or emergent, the universe effectively observes its own behavior. Symmetry serves as a cosmic self-reference, a way for the physical world to maintain consistency across different contexts and transformations. The preservation of certain quantities amid change, the relationships between different forces and particles, the properties that remain invariant under various operations, all these represent the universe maintaining a coherent identity amid constant flux. Most remarkably, these symmetries are not imposed from outside, but appear to be intrinsic to the fabric of reality itself. The universe doesn't follow symmetric laws because some external agency decreed it. Rather, these symmetries emerge naturally from the mathematical structure of existence. In observing and discovering these symmetries, human consciousness participates in the universe's self-observation, recognizing patterns that have shaped cosmic evolution since the beginning of time. This self-observation through symmetry extends to the large-scale structure of the cosmos as well. The distribution of galaxies across space reveals patterns, filaments, walls, and voids that form the cosmic web. While not perfectly symmetric, this structure exhibits statistical regularities that encode information about the universe's composition, the nature of gravity, and the initial conditions after the Big Bang. The cosmos imprints its own properties onto its large-scale architecture, creating a spatial record of its evolution that astronomers can read and interpret. Perhaps the most profound example of cosmic self-reference through symmetry comes from the holographic principle, a theory suggesting that all the information contained in a volume of space can be encoded on its boundary surface. This principle, emerging from studies of black hole thermodynamics, implies a deep symmetry between volumes and surfaces, between three-dimensional physics and two-dimensional information. If correct, it would mean that the universe encodes multiple equivalent descriptions of itself, different mathematical formulations that capture the same physical reality from complementary perspectives. As we contemplate these nested layers of symmetry and self-reference, we confront a cosmos that doesn't merely exist, but seems organized according to patterns that enable it to maintain coherence across scales from the subatomic to the cosmic. The universe encodes its own behavior through conservation laws, preserves records of its history through broken symmetries, and establishes equivalences between seemingly different phenomena through transformational symmetries. This self-encoding doesn't require consciousness in any human sense, yet it represents a kind of cosmic self-observation, the universe maintaining consistency with itself, through mathematically precise relationships that persist across time, space, and transformation. When humans discover these symmetries through science, we're not imposing order on nature, but recognizing patterns that were already there, participating in the universe's ongoing process of self-reference. As you drift towards sleep, consider that the symmetries governing cosmic behavior, from the conservation of energy to the equivalence of reference frames, represent ways the universe maintains its identity amid constant change. These aren't abstract mathematical curiosities, but profound principles etched into the very fabric of reality, enabling the cosmos to observe itself through the balance of its own structure. In the dance of particles and the curvature of space-time, in the conservation of fundamental quantities and the breaking of primordial symmetries, the universe not only exists but encodes its own nature, creating a self-referential system of extraordinary elegance and depth. Among the most intriguing possibilities in our universe are temporal paradox situations, where cause and effect seem to circle back on themselves, creating loops in the fabric of time itself. While our everyday experience presents time as flowing in one direction only, certain theories in physics suggest that time might behave in far more complex ways, potentially allowing information or effects to travel backward or create closed time-like curves where an event can be both cause and consequence of itself. These time loops, though speculative, aren't merely the stuff of science fiction. They emerge naturally from some of our most sophisticated theoretical frameworks, particularly Einstein's general relativity. This theory, which describes gravity as the curvature of space-time by matter and energy, allows for exotic solutions where space-time bends back upon itself, creating paths that return to their starting points not just in space, but in time as well. One such solution was discovered by mathematician Kurt Gödel in 1949. Gödel, better known for his incompleteness theorems in mathematical logic, found that Einstein's equations permitted a rotating universe in which it would be possible to travel into one's own past. Though our universe doesn't appear to rotate in the way Gödel's solution requires, the discovery was profound. It demonstrated that closed time-like curves are compatible with the mathematics of general relativity. Other theoretical scenarios for time loops have emerged since then. Wormhole hypothetical tunnels through space-time could potentially connect different regions of space and different moments in time. If stable, traversable wormholes could exist, they might allow for journeys that end before they begin, creating closed loops in causality. Similarly, certain arrangements of cosmic strings, theoretical defects in space-time left over from the early universe, might bend space and time enough to create paths that circle back to their temporal starting points. While these possibilities remain theoretical, they raise profound questions about causality and the nature of time itself. If time loops are possible, even in principle, they challenge our fundamental understanding of cause and effect. How can an effect precede its cause? How can information exist without ever having been created? These questions push against our intuitive understanding of temporal sequence, suggesting a cosmos where time operates not as a linear arrow, but as a complex landscape with loops, branches, and connections between different moments. Some physicists have proposed a chronology protection conjecture, suggesting that the laws of physics would somehow prevent closed time-like curves from forming, thus protecting causality from paradoxes. According to this view, quantum effects would intervene as a wormhole or other time-bending structure began to form, preventing it from creating a complete loop in time. The universe, in effect, would censor itself, prohibiting configurations that would violate causality. Others have explored the implications of time loops within quantum mechanics, finding that quantum particles behave differently in the presence of closed time-like curves, potentially resolving paradoxes through the probabilistic nature of quantum states. In the Deutsch model, named after physicist David Deutsch, particles traveling along closed time-like curves would be constrained to behave consistently with their future interactions with themselves, automatically avoiding contradictions. These theoretical explorations, while speculative, suggest that the universe might permit feedback across time under certain circumstances, allowing effects to influence their own causes in a closed loop of causality. The cosmos would effectively observe its own future and adjust its present accordingly, creating a self-consistent cycle that avoids logical contradictions. Even without dramatic wormholes or cosmic strings, subtler forms of temporal feedback might operate in our universe. Consider the delayed choice quantum eraser experiment, where the decision to measure which path a particle takes seems to retroactively determine whether it previously behaved as a wave or a particle. While interpretations vary, some suggest that future observations can influence past behaviors, creating a kind of temporal loop at the quantum level. On cosmic scales, the expansion of the universe itself involves complex feedback mechanisms. The rate of expansion at any moment affects the future distribution of matter and energy, which in turn influences the subsequent expansion rate. In models of cosmic inflation, a period of exponential expansion in the universe's first fraction of a second, quantum fluctuations that started as microscopic variations were stretched to cosmic scales, eventually seeding the formation of galaxies and clusters. These structures then affected the later expansion of the universe, creating a feedback loop across vast spans of time. Dark energy, the mysterious force accelerating the universe's expansion, adds another layer to this cosmic feedback. As the universe expands faster, galaxies move away from each other more rapidly, reducing their gravitational influence on each other. This reduced gravitational interaction allows for even faster expansion, creating a self-reinforcing cycle that drives the universe toward an increasingly sparse and cold future. Some cosmological models even suggest more exotic possibilities. In cyclic universe theories, the cosmos oscillates between periods of expansion and contraction, potentially allowing information or influences to propagate from one cycle to the next. While not true time loops in the sense of returning to the exact same moment, these cycles would create a form of cosmic memory, where patterns or structures from previous cycles might leave imprints on subsequent ones. The anthropic principle, mentioned in an earlier chapter, also involves a kind of cosmic feedback loop. It suggests that the parameters of our universe must be compatible with the eventual emergence of observers, since otherwise, no one would be around to measure them. This creates an observational selection effect. We can only find ourselves in a universe capable of producing observers that links the cosmos's initial conditions to the eventual emergence of consciousness billions of years later. Quantum cosmology takes this idea further. In the Wheeler-DeWitt equation, which attempts to apply quantum mechanics to the entire universe, the cosmos exists in a superposition of different possible states. Some interpretations suggest that observations made by conscious entities within the universe help select or emphasize particular branches of this cosmic wave function, creating a feedback loop between observation and cosmic reality. The universe's state affects the emergence of observers, whose observations then influence which aspects of the universe's wave function become emphasized. The concept of cosmic natural selection, proposed by physicist Lee Smolin, suggests another kind of temporal feedback across multiple universes. In this speculative theory, black holes might give birth to new universes, with slight variations in their physical constants. Universes that produce more black holes would generate more offspring universes, creating an evolutionary pressure toward physical laws that maximize black hole production. Since the conditions favorable for black hole formation also happen to be favorable for the emergence of complex chemistry and potentially life, this cosmic reproduction cycle might explain why our universe seems fine-tuned for complexity. Even the apparent flow of time itself might involve feedback mechanisms. The second law of thermodynamics, which defines the arrow of time through increasing entropy, is ultimately statistical in nature. Systems tend to evolve from less probable to more probable states, but these probabilities depend on the boundary conditions of the universe, particularly its extraordinarily low entropy beginning. This initial state creates the conditions for entropy to increase, which in turn defines the direction we experience as forward in time. The arrow of time emerges from a cosmic feedback loop between initial conditions and statistical evolution. Some physicists have proposed that the perception of time's flow might involve quantum measurement processes in the brain, potentially connecting our subjective experience of time to the same quantum phenomena that create the measurement problem in physics. If true, this would suggest a deep connection between consciousness, observation, and temporal experience, another form of feedback between observers and the cosmic conditions that make observation possible. While many of these scenarios remain speculative, they all point to a universe more complex than our intuitive sense of linear time suggests. The cosmos may contain nested feedback loops where future states influence past ones, where observation affects the thing observed, and where causality operates not just in straight lines but in circuits that double back on themselves. This perspective invites us to reconsider the relationship between time and information. If information can loop back through time under certain conditions, then the universe might encode a kind of memory of its own future, not in the sense of predetermined destiny, but as a pattern of constraints and consistencies that shape cosmic evolution. The universe would observe not just its past but aspects of its future as well, creating a self-consistent cycle of causality that transcends our usual understanding of temporal sequence. Interestingly, these potential time loops echo ancient philosophical conceptions of cyclical time found in many cultures. From the Ouroboros the serpent, eating its own tail, to the concept of eternal return, human intuition has long suggested that time might fold back upon itself, creating patterns of recurrence and self-reference. Modern physics offers mathematical frameworks that give these ancient intuitions new precision, suggesting ways that the cosmos might indeed circle back upon itself through the curvature of space-time or the probabilistic nature of quantum events. As you contemplate these possibilities, remember that even without literal time travel, our universe demonstrates remarkable temporal connectivity. Light from distant galaxies brings us images from billions of years in the past. The atoms in your body were forged in stars that died long before Earth formed. The cosmic microwave background radiation surrounds us with light from the universe's infancy. These connections across time don't require exotic wormholes or closed time-like curves. They emerge naturally from the finite speed of light and the evolutionary history of matter. Perhaps the most remarkable time loop of all is consciousness itself, the fact that the universe has evolved systems capable of reconstructing its history, modeling its present, and projecting its future. Through science, art, and imagination, conscious beings create internal representations of cosmic history that loop from the Big Bang through billions of years of evolution to the present moment, and then extend forward into possible futures. This cognitive modeling creates a kind of virtual time loop, where the end product of cosmic evolution, consciousness, contemplates its own origins and the processes that produced it. When you observe the night sky, tracing the light from ancient stars back to its origins, you're completing a circuit of information that connects your present moment to events billions of years in the past. Your observations don't change those distant events, but they bring them into your conscious experience, creating a connection across time that would not otherwise exist. In this sense, every act of astronomical observation creates a loop between present and past, between observer and the cosmic conditions that made observation possible. As our understanding of physics continues to evolve, we may discover new ways in which time loops and cosmic feedback shape the universe's behavior. Whether through the exotic possibilities of closed time-like curves or the subtler feedback between observation and quantum states, these temporal connections suggest a cosmos more intricately self-referential than our everyday experience indicates. The universe may not merely unfold in a linear progression from past to future, but exist as an interconnected whole, with information flowing not just forward in time, but potentially in loops and circuits that transcend simple temporal sequence. This perspective doesn't require abandoning causality. Indeed, the most compelling theories of time loops emphasize self-consistency, where cause and effect still operate, but in circuits rather than straight lines. When we gaze at a distant galaxy through our telescopes, we're seeing light that has traveled across vast stretches of space and time to reach us. But before that light began its journey to Earth, it participated in a complex dance within the galaxy itself, bouncing between stars and gas clouds, being absorbed and re-emitted, scattered and focused by the galaxy's own structure. A galaxy doesn't simply radiate light outward like a bare light bulb. It illuminates itself through intricate processes of internal reflection, absorption, and re-emission that shape both its appearance and its physical evolution. At the heart of this self-illumination is star formation, the process by which clouds of gas collapse under their own gravity to create new stars. These stellar nurseries are typically found within dense molecular clouds, which are themselves nested within the larger structure of a galaxy's spiral arms or central regions. As stars form within these clouds, their intense radiation begins to interact with the surrounding material, creating a feedback loop that transforms both the stars and their environment. Newly formed stars, particularly the massive, hot ones, flood their surroundings with ultraviolet radiation that ionizes nearby hydrogen gas, creating glowing regions called H2 regions, pronounced H2. These colorful nebulae, such as the famous Orion Nebula in our own Milky Way, represent areas where the galaxy is quite literally lighting itself from within. The intense radiation from young stars causes the surrounding gas to glow like a fluorescent light, converting invisible ultraviolet light into the visible pinks and reds that characterize these star-forming regions. This process isn't just visually striking, it's a fundamental part of how galaxies regulate their own evolution. As stars illuminate the gas around them, they also heat it, creating pressure that can prevent further gravitational collapse in neighboring regions. This negative feedback helps control the pace of star formation, preventing the galaxy from converting all its gas into stars at once. At the same time, the radiation and stellar winds from massive stars can compress gas at the edges of these illuminated regions, potentially triggering new generations of star formation in a process called sequential or induced star formation. Beyond the immediate vicinity of young stars, galaxies contain vast clouds of dust-tiny solid particles made primarily of carbon and silicates. Though they constitute only about 1% of the interstellar medium by mass, these dust grains play a crucial role in how galaxies illuminate themselves. Dust absorbs and scatters light, particularly at blue and ultraviolet wavelengths, causing distant stars to appear redder than they actually are, a phenomenon known as interstellar reddening. This selective absorption reshapes the light traveling through the galaxy. Blue light from distant stars gets absorbed by dust, then re-radiated as infrared heat. This transformation shifts energy from visible wavelengths to infrared, making galaxies appear different depending on the wavelength of observation. A spiral galaxy that shows distinct blue spiral arms in visible light will reveal a more uniform glow in infrared, as the dust heated by absorbed starlight re-emits that energy evenly across the galaxy's structure. The dust doesn't merely absorb light, it scatters it as well, creating subtle but significant effects. When starlight encounters dust particles, some photons are redirected rather than absorbed, changing their direction of travel while maintaining their wavelength. This scattering creates reflection nebulae, bluish clouds that shine with light borrowed from nearby stars. Unlike the reddish emission nebulae, which glow with their own transformed energy, reflection nebulae act like cosmic mirrors, redirecting stellar illumination through the galaxy's structure. Particularly striking examples of galactic self-illumination occur when stars form in the dense dust lanes that trace spiral arms. These young, hot stars illuminate the very structures that gave birth to them, causing spiral arms to glow with both direct starlight and the light reprocessed by surrounding gas and dust. The arms become visible not just because they contain stars, but because they contain the right arrangement of stars, gas, and dust to efficiently capture and transform light within the galaxy's own structure. In more dramatic cases, bursts of star formation can illuminate entire galaxies from within. Starburst galaxies experience intense episodes of star formation, often triggered by interactions with neighboring galaxies. These cosmic collisions compress gas throughout the affected galaxies, spawning thousands or even millions of new stars in a relatively short cosmic timespan. The resulting stellar newborns flood their galaxies with radiation, causing gas to glow and dust to heat up, dramatically increasing the galaxy's overall brightness and changing their appearance across the electromagnetic spectrum. The self-illumination of galaxies extends beyond visible light. Young, massive stars produce copious amounts of ultraviolet radiation, which ionizes gas and energizes electrons in dust grains. When these electrons return to their ground state, they can emit photons at specific wavelengths, creating spectral emission lines that serve as diagnostics of the physical conditions within the galaxy. By analyzing these lines, astronomers can determine the temperature, density, and chemical composition of the illuminated material, reading the galaxy's internal conditions from the light it processes and transforms. At radio wavelengths, galaxies illuminate themselves through entirely different mechanisms. Cosmic ray-shy energy particles, accelerated by supernova explosions and other energetic events, spiral around magnetic fields, producing synchrotron radiation that permeates the galaxy. This radio emission traces the galaxy's magnetic field structure, revealing patterns invisible at other wavelengths. The galaxy effectively lights itself up at radio frequencies by converting the kinetic energy of these particles into electromagnetic radiation as they travel through its magnetic architecture. Perhaps the most dramatic example of galactic self-illumination occurs in active galactic nuclei, AGN, the extraordinarily energetic cores of galaxies powered by supermassive black holes. As matter falls toward these black holes, it forms an accretion disk that heats to millions of degrees, emitting intense radiation across the electromagnetic spectrum. This radiation doesn't just escape directly to space, it interacts with the surrounding gas and dust, creating complex structures of illuminated material. In some AGN, clouds of gas orbit the central black hole at high speeds, becoming illuminated by the intense radiation from the accretion disk. These clouds absorb and re-emit this energy at specific wavelengths, creating bright emission lines that allow astronomers to study the conditions and motion of material in these extreme environments. The black hole, though invisible itself, illuminates its surroundings through the energy released by matter falling into its gravitational grasp. In the most powerful AGN, called quasars, the central black hole can outshine all the stars in the host galaxy combined. The intense radiation from the quasar illuminates not just the host galaxy, but can extend its influence into intergalactic space, ionizing gas clouds at distances of hundreds of thousands of light years. These illuminated clouds, visible as extended emission line regions, reveal the reach of the quasar's influence and provide information about the distribution of gas in the otherwise invisible cosmic web. Galaxies also illuminate themselves through more temporary events. When a massive star ends its life in a supernova explosion, it releases an enormous amount of energy in a brief flash, briefly outshining the entire galaxy. This intense burst of radiation illuminates the surrounding interstellar medium, revealing structures that would otherwise remain invisible. As the supernova's light echoes outward, reflecting off dust clouds at different distances, it creates expanding shells of illumination that allow astronomers to map the three-dimensional distribution of dust around the explosion site. Similarly, when stars are torn apart by the tidal forces of supermassive black holes in events called tidal disruption events, the resulting flash of radiation can illuminate previously unseen regions of the galaxy. These rare events provide unique opportunities to probe the environment around normally quiescent black holes as the sudden burst of light interacts with and illuminates the surrounding material. The internal illumination of galaxies affects not just their appearance, but their physical evolution as well. As stars form and illuminate their surroundings, they inject energy into the interstellar medium, heating it and creating pressure that supports the galaxy against gravitational collapse. This stellar feedback is crucial for regulating star formation and maintaining the galaxy's overall structure. In spiral galaxies, the pattern of self-illumination reinforces the very structures that shape the galaxy. Stars forming in spiral arms illuminate the arms themselves, making them more visible while also heating the gas and preventing it from collapsing too quickly. This feedback loop helps maintain the spiral pattern over billions of years, despite the differential rotation that would otherwise wind up and destroy the spiral structure within a few rotations. The self-illumination of galaxies also creates a form of cosmic memory, as light absorbed by dust is re-emitted at infrared wavelengths over extended periods. The infrared glow of a galaxy doesn't just reflect its current state, but integrates over its recent star formation history, preserving information about stellar populations that formed over the past few million years. The galaxy effectively remembers its recent past through the thermal radiation of dust heated by generations of stars. Even the darkest regions of galaxies participate in this self-illumination. Dark, nebula-dense clouds of dust that appear as silhouettes against brighter backgrounds shape a galaxy's appearance by selectively blocking light. These dark regions aren't truly dark in an absolute sense. They're illuminated from within by embedded stars, and from without by the general galactic light field. Their apparent darkness is relative, a contrast effect that reveals the three-dimensional structure of the galaxy's dust distribution. Our own Milky Way provides a unique perspective on galactic self-illumination, as we observe it from within rather than from outside. The band of light stretching across our night sky represents our edge-on view of our galaxy's disk, with its complex patterns of emission and absorption. Dark dust lanes cut through the glowing band, while bright star-forming regions create patches of enhanced brightness. This intricate interplay of light and shadow reveals the structure of our galactic home through its internal pattern of illumination. Advanced simulations now allow astronomers to model how galaxies illuminate themselves, accounting for the complex interactions between stars, gas, and dust. These models track photons as they travel through the simulated galaxy, bouncing off dust grains, being absorbed and re-emitted, and gradually working their way through the galactic structure. By comparing these simulated patterns of illumination with observations, astronomers can refine their understanding of the processes that shape galactic appearance and evolution. One particularly interesting aspect of galactic self-illumination is how it creates different appearances at different wavelengths. A galaxy observed in ultraviolet light reveals the distribution of recent star formation, as young, hot stars dominate at these wavelengths. The same galaxy in visible light shows a blend of stellar populations of various ages. In infrared, the galaxy's appearance is dominated by the warm glow of dust heated by absorbed starlight, while radio observations reveal synchrotron emission from cosmic rays traveling through magnetic fields. Each wavelength regime tells a different part of the story, revealing how the galaxy processes and transforms energy from one form to another. This wavelength-dependent appearance creates a form of cosmic spectroscopy, where the galaxy's structure acts as a prism, separating the different components of its energy output. By combining observations across the electromagnetic spectrum, astronomers can reconstruct the galaxy's internal processes, from star formation to supernova explosions, to the flow of material into central black holes. The study of how galaxies illuminate themselves connects to broader questions in cosmology. The light emitted and transformed by galaxies contributes to the cosmic background radiation at various wavelengths, from the ultraviolet to the far infrared and radio. By understanding how individual galaxies process light internally, astronomers can better interpret the composite glow from billions of galaxies that constitutes these cosmic backgrounds. As you drift towards sleep tonight, consider the fact that the distant galaxies visible through telescopes aren't just passive objects being illuminated from outside. They're dynamic systems that glow from within, their appearance shaped by the complex interaction of stars, gas, and dust that transform and redirect light. When we observe a galaxy, we're seeing not just the sum of its stars, but the result of a cosmic light show where radiation is absorbed, scattered, and re-emitted in an intricate dance that reveals the galaxy's structure and history. Throughout human history, we have used the light of stars to navigate our world. Ancient sailors followed the steady North Star across vast oceans, and early civilizations tracked the movements of planets against the fixed backdrop of constellations to mark the seasons. But in modern cosmology, the relationship between light and navigation has grown far more profound. Today, astronomers use the ancient light crossing the cosmos to construct detailed maps, not just of where objects are, but of how the entire universe is structured through both space and time. This cosmic cartography begins with a simple but astonishing fact. Light travels at a finite speed, 299, 792, 458 meters per second in vacuum. This means that looking into space is literally looking back in time. The light from the moon takes 1.3 seconds to reach us. Sunlight takes about 8 minutes, and light from the nearest star system, Alpha Centauri, requires 4.3 years. When we observe distant galaxies, we're seeing them as they were millions or billions of years ago, when the light now entering our telescopes first began its journey across the cosmos. This time delay creates a natural organizing principle for mapping the universe. By measuring the distances to cosmic objects, astronomers can arrange them in three-dimensional space, with the third dimension representing time as well as distance. Nearby galaxies appear as they were relatively recently, while the most distant observable objects show us the universe as it was shortly after the Big Bang. The entire observable universe becomes a time-ordered map, with each distance corresponding to a specific epoch in cosmic history. The light itself carries the information needed to determine these distances. As the universe expands, it stretches the wavelengths of light traveling through it, shifting them toward the red end of the spectrum of phenomenon known as cosmological redshift. By measuring how much a galaxy's light has been redshifted, Astronomers can calculate how much the universe has expanded since that light began its journey, which in turn reveals the galaxy's distance and the cosmic epoch it represents. This redshift distance relationship transforms the ancient light, crossing the cosmos into a natural coordinate system. Astronomers speak of observing the universe at different redshifts, with higher redshifts corresponding to greater distances and earlier cosmic times. A galaxy at redshift 1 is seen as it appeared when the universe was about half its current age. A quasar at redshift 6 shows us the cosmos when it was less than 1 billion years old. The cosmic microwave background, with a redshift of about 100, reveals the universe as it was just 380 years after the Big Bang. With this framework in place, astronomers can begin mapping the large-scale structure of the universe, the vast network of galaxy filaments, clusters, and voids that forms the cosmic web. By surveying hundreds of thousands or even millions of galaxies, measuring their positions and redshifts, researchers construct three-dimensional maps that reveal how matter is distributed across billions of light-years of space. These maps show that galaxies aren't scattered randomly throughout the universe, but instead form a complex, sponge-like structure. Dense clusters of galaxies are connected by filaments-long, thread-like arrangements of galaxies, and gas which in turn surround vast, nearly empty voids. This cosmic web emerged from tiny density fluctuations in the early universe, gradually amplified by gravity over billions of years of cosmic evolution. The light from distant galaxies doesn't just reveal their positions, it also contains information about their properties and histories. By analyzing the spectrum of a galaxy's light, breaking it down into its component wavelengths, astronomers can determine its chemical composition, star formation rate, and even the properties of any supermassive black hole that might lurk at its center. This spectroscopic information adds layers of detail to the basic map, transforming it from a simple plot of positions to a rich dataset that encodes the evolutionary history of cosmic structure. The mapping process extends beyond visible galaxies to include matter that doesn't emit light directly. Dark matter, which makes up about 85% of the universe's mass but doesn't interact with electromagnetic radiation, can be mapped through its gravitational effects on visible matter and light. By observing how galaxy clusters bend the light from more distant objects, a phenomenon called gravitational lensing, astronomers can construct maps of the invisible dark matter scaffolding that underlies the cosmic web. Even the gas between galaxies, the intergalactic medium, can be mapped using the light from distant quasars. As this light travels toward Earth, it passes through clouds of hydrogen gas that absorb specific wavelengths, creating a pattern of absorption lines called the Lyman alpha forest. Each absorption line represents a hydrogen cloud at a specific distance, allowing astronomers to map the distribution of gas along the line of sight to the quasar. By combining observations of many quasars, researchers can reconstruct the three-dimensional distribution of intergalactic gas across cosmic time. These mapping techniques have revealed that the universe has a complex history of structural evolution. In the early cosmos, matter was distributed fairly uniformly, with only slight variations in density from one region to another. As the universe expanded and cooled, gravity gradually amplified these variations, pulling matter toward the denser regions and away from less dense ones. Over billions of years, this process transformed the nearly smooth early universe into the richly structured cosmic web we observe today. The maps constructed from ancient light also reveal how this structure formation process was influenced by the mysterious dark energy that now dominates the universe's energy budget. By comparing the clustering of galaxies at different cosmic epochs, astronomers can track how the growth of structure has changed over time. These observations show that about 5 billion years ago, dark energy began to overpower gravity on the largest scales, causing the expansion of the universe to accelerate and slowing down the formation of new cosmic structures. Perhaps the most remarkable aspect of these cosmic maps is that they allow us to trace the universe's history backward, reconstructing earlier states from observations of its current condition. By modeling how gravity would have shaped the observed distribution of matter over time, cosmologists can rewind the cosmic film, calculating how the universe must have looked at earlier times to evolve into what we see today. This process has allowed astronomers to map the initial conditions of the universe with extraordinary precision. The tiny density fluctuations that seeded all cosmic structure have been reconstructed from observations of galaxies, clusters, and the cosmic microwave background. These primordial variations, quantum fluctuations stretched to cosmic scales during the inflationary epoch, represent the original blueprint from which all later structure developed. The ancient light crossing the cosmos thus becomes not just a map of where things are, but a record of how they came to be. Each photon reaching our telescopes carries information about the conditions it encountered on its journey, the clouds it passed through, the gravitational fields that deflected its path, the expansion of space that stretched its wavelength. By analyzing this light in detail, astronomers reconstruct the history of the universe from its earliest moments to the present day. This cosmic cartography continues to advance as technology improves. New telescope arrays survey ever larger volumes of space with greater precision. Powerful computer simulations model how the observed structures would have evolved from various initial conditions, allowing researchers to test different cosmological theories against the actual data. Machine learning algorithms help identify patterns in the vast datasets generated by these surveys, extracting subtle signals that might otherwise be overlooked. Future projects promise even more detailed maps. The Vera C. Rubin Observatory, currently under construction in Chile, will conduct a 10-year survey of the southern sky, observing billions of galaxies and measuring their properties with unprecedented precision. The Nancy Grace Roman Space Telescope, scheduled for launch later this decade, will use both galaxy positions and weak gravitational lensing to map the distribution of dark matter across cosmic time. The DESI, Dark Energy Spectroscopic Instrument, will measure precise redshifts for tens of millions of galaxies, creating the most comprehensive map yet of the universe's expansion history. These mapping efforts connect directly to fundamental questions in cosmology. How did the universe begin? What is it made of? How will it evolve in the future? The light from distant sources, gathered and analyzed through increasingly sophisticated methods, provides the data needed to address these profound mysteries. The ancient photons crossing the cosmos become not just messengers from the past, but guides to understanding the nature of reality itself. As you contemplate the night sky, consider that the light reaching your eyes is not merely illuminating the darkness, but carrying a map of cosmic history, a chart of how matter has organized itself across billions of years of evolution. The universe has written its autobiography in light, and astronomers have learned to read this luminous text, deciphering the story of a cosmos that transformed from near uniformity to rich complexity through the patient work of gravity over countless eons. In this way, the light from the past doesn't just show us where things were, it reveals the underlying patterns and processes that shaped our universe. The cosmos becomes not just a collection of objects, but a coherent system with its own history and structure, revealed to us through the ancient light that continues its journey across the vastness of space and time. Look up at the night sky. That seemingly empty darkness between the stars isn't empty at all, it's filled with light. Photons from every star, galaxy, and cosmic event that has ever been visible from Earth are still traveling through space, carrying with them perfect records of their origins. In a very real sense, the sky is an immense archive containing the complete history of the observable universe, with each photon serving as a tiny data packet encoded with information about its source. This cosmic archive operates on a scale that dwarfs any human record-keeping system. Every second, approximately 10-18 photons, a billion particles of light from beyond our solar system, pass through a space the size of a human pupil. Each carries specific information: the element that emitted it, the temperature and density of its source, the gravitational fields it passed through, the gas clouds that partially absorbed it, and the precise moment it began its journey through space. Unlike human archives, which are curated and organized, the universe's light-based record system has no librarian or filing system. The information is preserved with perfect fidelity. Light doesn't degrade or corrupt as it travels through the vacuum of space, but it's not arranged for ease of access. Photons from different cosmic epochs mix together, arriving at Earth in no particular order, except that determined by the distance of their sources and the intervening matter they encountered. Yet astronomers have developed ingenious methods to extract and organize this information, essentially serving as interpreters who can read the universe's luminous archive. Spectroscopist's technique of splitting light into its component wavelengths allows researchers to determine the chemical composition of objects billions of light-years away. The specific wavelengths absorbed or emitted by different elements create unique spectral fingerprints that identify the atomic and molecular makeup of distant stars, galaxies, and gas clouds. These spectral signatures tell us not just what distant objects are made of, but also their physical conditions. The precise wavelengths of emission and absorption lines reveal temperature, density, and even the magnetic fields present in the source. The width of these lines indicates how fast the material is moving and whether it's being compressed or stretched by gravitational forces. From just a few photons, astronomers can reconstruct detailed information about objects too distant to visit in person. The Cosmic Archive preserves records of events both routine and catastrophic. When a massive star explodes as a supernova, the flash of light carries specific information about the explosion's energy, the elements created in the stellar furnace, and the structure of the dying star. This light continues traveling outward forever, creating an expanding sphere of information that grows larger with each passing second. Even billions of years later, that record remains intact, waiting for someone or something to intercept and read it. Even more remarkably, the light from transient event supernovae, gamma-ray bursts, neutron star mergers creates a kind of three-dimensional hologram expanding through space. Observers at different distances from the event would see it at different times, creating a permanent record distributed through space itself. If technological civilizations exist throughout our galaxy, they could potentially combine their observations of such events, each made at different times, to reconstruct the event in extraordinary detail. The universe's light-based archive extends far beyond the visible spectrum. Radio waves from the earliest stars, infrared radiation from dust-shrouded galaxies, X-rays from material falling into black holes, gamma rays from the most energetic cosmic processes all travel through space, carrying information about their sources. By developing instruments sensitive to these different forms of light, astronomers have learned to access portions of the cosmic archive that would remain invisible to human eyes alone. This multi-wavelength approach has revealed that the universe keeps different kinds of records in different parts of the electromagnetic spectrum. Optical light typically shows us the stellar populations of galaxies. Infrared radiation reveals regions of star formation hidden behind dust clouds. X-rays map the superhot gas in galaxy clusters and the environments around black holes. Radio waves trace magnetic fields and the synchrotron radiation from electrons spiraling through space. Together, these different documents in the Cosmic Archive tell a more complete story than any single wavelength could provide. The cosmic microwave background radiation represents perhaps the oldest and most comprehensive document in this universal archive. These ancient photons, released when the universe first became transparent about 380 years after the Big Bang, have been traveling through space ever since, gradually stretched by cosmic expansion until they now fall in the microwave portion of the spectrum. The slight temperature variations in this radiation differences of just 1 part in 100 preserve a perfect record of the density fluctuations in the early universe, the seeds from which all structure would eventually grow. But the universe's record-keeping doesn't stop with electromagnetic radiation. Cosmic ray-shy energy particles accelerated by supernovae, black holes, and other powerful sources also carry information across vast distances. These particles, primarily protons and atomic nuclei, preserve details about the most energetic processes in the cosmos, though their paths are bent by magnetic fields, making it harder to trace them back to specific sources. More exotic messengers are also part of this cosmic archive. Neutrinos, nearly massless particles that barely interact with normal matter, travel unimpeded from the cores of stars and supernovae, carrying information from regions that even light cannot escape directly. Gravitational waves ripples in space-time, caused by the acceleration of massive objects, provide yet another record system, preserving the dynamics of colliding black holes, neutron stars, and potentially other violent cosmic events. What makes the universe's archive truly extraordinary is that it preserves information from all times simultaneously. The light from nearby stars shows them as they were just years or decades ago. The light from distant galaxies reveals them as they existed millions or billions of years in the past. By observing objects at different distances, astronomers effectively access different moments in cosmic history, all preserved in the light still traveling through space. This temporal dimension of the cosmic archive allows astronomers to study how the universe and its contents have evolved over time. By comparing galaxies at different distances, and therefore different ages, researchers can track how star formation rates, chemical compositions, and galactic structures have changed throughout cosmic history. The universe hasn't just preserved static records of individual objects, it's maintained a continuous narrative of its own development. In some cases, the archive even preserves multiple images of the same object from different times in its history. When light from a distant quasar is bent around a massive galaxy cluster through gravitational lensing, it can follow different paths of different lengths, creating multiple images that show the quasar at different moments in its evolution. These cosmic time capsules allow astronomers to witness how active galactic nuclei change over periods of months or years, despite the fact that the light has been traveling for billions of years to reach us. The universe's archival system doesn't just record objects and events, it preserves patterns and relationships as well. The distribution of galaxies across space forms a vast cosmic web, with filaments, clusters, and voids creating a sponge-like structure that extends for billions of light-years in all directions. This pattern, visible only when thousands or millions of galaxies are mapped together, reveals how gravity has shaped the universe's large-scale structure over billions of years of evolution. Even empty regions of the cosmic archive contain information. The radiation passing through apparently vacant areas of space often shows absorption features, specific wavelengths removed by gas too diffuse to see directly. This cosmic barcode reveals the presence, composition, temperature, and motion of gas clouds that would otherwise remain invisible. The seemingly empty regions between galaxies, rather than being blank pages in the cosmic record, contain subtle but information-rich signatures of the intergalactic medium. Perhaps most remarkably, the universe's light-based archive preserves quantum information as well. When particles become entangled, their quantum states become correlated regardless of the distance between them. This spooky action at a distance, as Einstein called it, means that information about one particle's state is instantly reflected in its entangled partner, even if they're separated by the width of the universe. This quantum connectedness creates another layer of cosmic record-keeping, one that operates outside the normal constraints of space and time. As you gaze at the stars tonight, consider that the universe has been maintaining its luminous archive since the first atoms formed and space became transparent to radiation. Every photon that has ever been emitted by a star and not absorbed by intervening matter is still traveling somewhere in the cosmos, carrying its tiny packet of information further into space with each passing second. The history of the universe isn't lost to time, it's preserved in an ever-expanding sphere of light that grows larger with each moment. This perspective transforms our understanding of cosmic history. The past isn't gone, it's encoded in radiation still traveling through space. The light from the first stars still exists, though it has now been stretched to wavelengths too long for our current instruments to detect. The flash from every supernova, the glow from every galaxy, the radiation from every cosmic evental continue their journey outward, permanent records in the universe's light-based archive. In the vastness of cosmic space, there exists a boundary beyond which we cannot see a horizon that marks the limits of our observable universe. This boundary isn't a physical wall or barrier, but rather the maximum distance from which light has had time to reach us since the beginning of the universe. Everything beyond this cosmic horizon remains forever invisible to us, not because it doesn't exist, but because its light simply hasn't had enough time to complete the journey to Earth. This cosmic horizon sits approximately 46.5 billion light-years away in all directions, forming an immense sphere with Earth at its center. The radius might seem surprisingly larger than the 13.8 billion years that represent the age of the universe, but this discrepancy arises because space itself has been expanding as light travels through it. The most distant photons we can observe have been surfing the expanding fabric of the cosmos, carried along by the stretching of space-time even as they race toward us at the speed of light. What makes this boundary remarkable is that it functions as a kind of mirror frame, defining the limits of what we can observe and thus shaping our understanding of the cosmos. Just as a picture frame determines which portion of a scene is captured in a photograph, the cosmic horizon establishes which parts of the universe can be included in our cosmic portrait. Everything beyond remains unseen, potentially infinite in extent, but perpetually outside our observational reach. Unlike most frames, however, this one changes with time. Each day, photons from slightly more distant regions finally complete their journey to Earth, incrementally expanding our observable universe. The cosmic horizon isn't static but dynamic, growing at the speed of light as the universe ages. If we could somehow live for billions more years, we would gradually see more and more of the cosmos revealed, as light from increasingly distant regions finally reached our telescopes. Yet despite this growth, there are regions of the universe we will never see, due to the accelerating expansion of space, driven by the mysterious force called dark energy. Some galaxies are receding from us faster than the speed of light, when that recession is measured relative to the expanding space between us. Light emitted by these galaxies now will never reach us, no matter how long we wait. The observable universe has a maximum potential size, beyond which information cannot travel across the expanding gulf of space. This makes our cosmic horizon not just a temporal boundary, but a permanent one as well. Galaxies currently just beyond our horizon that would have eventually become visible in a universe with constant expansion will now remain forever hidden in our accelerating cosmos. The frame of our cosmic mirror is both expanding in the short term and fundamentally limited in the long term. What lies beyond this boundary? The simplest answer, supported by both theoretical models and observational evidence of the universe's homogeneity, is simply more of the same. More galaxies, more clusters, more filaments and voids forming the cosmic web, extending perhaps infinitely beyond our ability to observe. The portion of the universe we can see appears remarkably uniform on the largest scales, suggesting that the unobservable regions likely follow similar patterns and principles. Some theories of cosmic inflation, a period of exponential expansion in the earliest moments of the universe, suggest that the cosmos might be vastly larger than the part we can observe, perhaps by a factor of 10, 26 or more. In such scenarios, our observable universe would be like a tiny island in an unimaginably vast ocean. Our cosmic horizon defining the limits of our island's shores, but telling us nothing about the true extent of the waters beyond. This perspective transforms the cosmic horizon from a simple boundary into something more profound, a frame that defines our cosmic reflection. Everything we can know about the universe through direct observation is contained within this horizon. All our cosmic maps, all our understanding of cosmic evolution, all our measurements of cosmic parameter soul are derived from the light that has had time to reach us from within this finite volume of space. The edge of the observable universe thus serves as a mirror frame in two senses. First, it literally frames what we can see, establishing the boundaries of our cosmic view. Second, and perhaps more profoundly, it frames our reflection of the cosmos, our scientific understanding of the universe as a whole, based on the finite sample we can observe. Just as a mirror's frame determines which portion of a room is reflected, our cosmic horizon determines which portion of the universe can be included in our scientific picture of reality. This framing effect has important implications for cosmology. When astronomers measure the universe's properties, its expansion rate, its average density, its distribution of matter, they must always remember that these measurements apply directly only to the observable portion. Extrapolating to the universe as a whole requires assuming that our observable region is representative of the larger cosmos, an assumption known as the cosmological principle. Fortunately, evidence supports this assumption. The distribution of galaxies and the properties of the cosmic microwave background radiation suggest that the universe is both homogeneous, the same in all locations, and isotropic, the same in all directions, when viewed on sufficiently large scales. This uniformity suggests that our cosmic frame captures a fair sample of the universe, allowing us to make reasonable inferences about the whole based on the part we can see. Yet the existence of the cosmic horizon still reminds us of the fundamental limits to our knowledge. No matter how powerful our telescopes become, they can never reveal what lies beyond the maximum distance from which light has had time to reach us. The unobservable universe remains the ultimate scientific frontier, a region we can model mathematically and explore theoretically, but never observe directly. This limitation doesn't just apply to distant space, but to the early universe as well. The cosmic microwave background radiation represents the earliest light we can detect, released when the universe was about 380 years old. Before this time, the cosmos was opaque to electromagnetic radiation, creating a kind of temporal horizon that prevents us from directly observing the universe's earliest moments. Our observable cosmos is thus framed not just spatially, but temporally as well, bounded both by the maximum distance and the earliest time we can observe. These boundaries create a four-dimensional frame around our cosmic reflection of volume of space-time, outside of which we cannot directly see. Within this frame lies everything we can know through observation. Beyond it lies everything we can only infer through theory and extrapolation. The edge of the observable universe becomes the boundary between empirical science and theoretical inference, between what we can measure and what we can only model. Yet even with these limitations, the frame of our observable universe encompasses an extraordinary amount. Within our cosmic horizon lie roughly 2 trillion galaxies, each containing billions or trillions of stars. The volume of space we can potentially observe contains more atoms than there are grains of sand on all the beaches of Earth. Our cosmic reflection, though framed and finite, captures an almost unimaginable expanse of space, time, and matter. The frame itself also tells us something profound about the universe. The very existence of a cosmic horizon emerges from the fact that the universe has a beginning in time and that light travels at a finite speed. In a static, eternal universe, light from every region would eventually reach every other region, and no such horizon would exist. Our cosmic frame is a direct consequence of the universe's finite age and evolutionary history. The horizon's precise distance, about 46.5 billion light-years, encodes information about cosmic expansion throughout the universe's history. By studying objects at different distances, and thus different look-back times, astronomers can reconstruct how the expansion rate has changed over billions of years. This history reveals the competing influences of matter, which slows expansion through gravitational attraction, and dark energy, which accelerates expansion through its negative pressure. The frame of our observable universe thus becomes more than just a boundary, it becomes a record of cosmic expansion itself. The relationship between an object's distance and its redshift, the stretching of its light by expanding space, varies depending on how the universe's expansion has changed over time. By measuring this relationship for objects at different distances, astronomers can determine the universe's composition and track its evolution from a matter-dominated past to a dark energy-dominated future. Perhaps most remarkably, the edge of the observable universe gives us a glimpse of our own cosmic origins. The most distant objects we can see existed during the universe's infancy, just a few 100 million years after the Big Bang. By observing these ancient systems, we witness the early stages of cosmic evolution, the formation of the first stars, the assembly of the first galaxies, the initial growth of the cosmic web. Our cosmic frame captures not just the current state of the universe, but its developmental history as well. This temporal aspect of our cosmic reflection raises profound questions about the nature of time and cosmic history. The light reaching us from the edge of the observable universe began its journey nearly 13.8 billion years ago, when the universe was just beginning to form its first structures. That light has been traveling through expanding space ever since, a perfect record of those ancient cosmic moments preserved across the vastness of time and space. In a very real sense, the different distances within our observable universe represent different epochs in cosmic history, all visible simultaneously from our unique vantage point. Nearby galaxies appear as they were relatively recently, while distant ones show us the universe as it existed billions of years ago. This cosmic time machine allows us to study the evolution of galaxies, the growth of large-scale structure, and the changing rate of star formation throughout cosmic history, framed within the limits of our observable universe. The concept of the cosmic horizon also reminds us of our peculiar place in the cosmos. Each location in the universe has its own observable region, its own cosmic horizon centered on that particular point. The observable universe centered on a galaxy a billion light-years away would include regions beyond our horizon, while missing parts of the cosmos that we can see. Each vantage point has its own cosmic frame, its own unique reflection of the universe. This multiplicity of cosmic frames highlights the relativity of cosmic knowledge. What we can know about the universe depends partly on where we are located within it. Had Earth formed in a different galaxy, our cosmic horizon would frame a different portion of the universe, potentially leading to slightly different measurements of cosmic parameters and a different perspective on cosmic history. The edge of the observable universe also serves as a frame for our understanding of cosmic expansion itself. The most distant objects we can see are currently moving away from us at speeds approaching the speed of light, their current recession embedded in the stretching of space itself. Beyond our horizon lie regions receding even faster, their motion relative to expanding space exceeding light speed and making them forever unobservable. This doesn't violate Einstein's special relativity, which prohibits matter from moving through space faster than light. The galaxies aren't moving through space at these extreme speeds. Rather, the space between galaxies is expanding, carrying them along in its flow. There's no local experiment these distant galaxies could perform that would reveal speeds greater than light. It's only in the global frame of the expanding universe, measured across billions of light years, that such apparent superluminal recession appears. The cosmic horizon thus frames our understanding of relativity as well, marking the boundary between regions where objects are receding from us at subluminal speeds and those where cosmic expansion creates apparent superluminal recession. This division has profound implications for the future of cosmic observations. Galaxies currently just within our horizon will eventually accelerate beyond it as dark energy drives cosmic expansion at an ever-increasing rate, gradually shrinking the volume of space from which new light can reach us. In the extremely distant future, trillions of years from now, this accelerating expansion will push almost all galaxies beyond our cosmic horizon. Any observers in that far future would see only their local galaxy group, with the rest of the universe having receded beyond the limits of observability. Their cosmic frame would be vastly smaller than ours, limiting their ability to understand cosmic history and structure. We live in a privileged cosmic epoch, where the observable universe still encompasses a representative sample of cosmic structure. This temporal framing adds another dimension to our cosmic reflection. Not only is our view of the universe framed spatially by the cosmic horizon, it's also framed temporally by the specific cosmic era in which we exist. Earlier observers would have seen a smaller volume of the universe, as less time had elapsed for light to travel. Future observers will potentially see a larger volume in the near term, but a smaller one in the distant future, as accelerating expansion pushes galaxies beyond the horizon. The edge of the observable universe also frames our understanding of cosmic homogeneity and the cosmological principle. Observations suggest that the universe is uniform on scales larger than about 300 million light-years, with a fairly even distribution of galaxies throughout space. This uniformity supports the assumption that our observable region is representative of the cosmos as a whole. Yet without the ability to see beyond our cosmic horizon, we cannot directly confirm this uniformity across truly universal scales. The frame of our observable universe thus marks the boundary between empirical confirmation and theoretical extrapolation. Within the frame, we can directly measure cosmic homogeneity. Beyond it, we must rely on the cosmological principle and the assumption that the same physical laws and conditions apply throughout the cosmos. Some theories suggest that regions far beyond our cosmic horizon might actually differ significantly from our observable universe. Inflationary models that allow for varying physical parameters could create a multiverse, where different regions have different fundamental constants, different physical laws, or different numbers of dimensions. If such theories are correct, our cosmic frame captures just one province in a vast and varied cosmic landscape. This possibility transforms the edge of the observable universe from a simple horizon into the boundary between known and unknown cosmologies. Within our frame lies a cosmos with specific values for fundamental constants like the strength of gravity, the mass of the electron, and the speed of light. Beyond might lie regions with entirely different physical parameters, perhaps supporting exotic forms of matter and energy unlike anything in our observable universe. Such speculations remain theoretical, but they highlight the profound significance of our cosmic frame. The edge of the observable universe doesn't just limit what we can see, it potentially limits our understanding of the full range of cosmic possibilities. Our scientific theories, derived from observations within our cosmic horizon, might apply to just a tiny portion of a much larger and more varied cosmos. This framing effect applies to our understanding of cosmic origins as well. The Big Bang theory describes the evolution of the observable universe from an initially hot, dense state to its current expanded form. But without the ability to see beyond our cosmic horizon, we cannot directly observe whether this origin event applies to regions beyond our observable universe, or whether different regions might have different cosmic histories. Some inflationary models suggest that our observable universe represents just one bubble in an eternally inflating cosmos, where new regions are constantly being formed from the inflating space between existing bubbles. If such models are correct, our cosmic frame captures just one among countless cosmic domains, each with its own beginning and evolution. The edge of our observable universe thus serves as a frame not just for our view of the cosmos, but for our scientific understanding of reality itself. Within this frame, we have constructed remarkably successful theoretical models that explain the universe's evolution from the Big Bang to the present day. Whether these models apply beyond our cosmic horizon, whether they describe the universe as a whole, or just our local region remains an open question. This uncertainty doesn't diminish the remarkable achievements of modern cosmology. Within the frame of our observable universe, we have mapped the cosmic microwave background radiation, traced the distribution of galaxies across billions of light years, measured the expansion of space with increasing precision, and reconstructed the universe's composition and evolutionary history with extraordinary detail. The frame of our observable universe has proven large enough to contain a representative sample of cosmic structure, allowing us to identify patterns and principles that likely apply throughout the cosmos. The cosmological models derived from observations within our horizon have made successful predictions about phenomena we subsequently observed, confirming their validity within the frame of our cosmic reflection. As you consider the night sky tonight, remember that what you see represents just a tiny fraction of the observable universe, which in turn may be just a tiny fraction of the cosmos as a whole. The edge of the observable universe forms a frame around everything we can directly know about the cosmos, a boundary set by the finite age of the universe and the finite speed of light. Within this frame lies a reflection of cosmic reality, as complete as the laws of physics allow us to see from our particular vantage point in space and time. Like a picture frame that focuses attention on the image it contains, the cosmic horizon focuses our scientific inquiry on the observable universe, while acknowledging the possibility of a larger reality beyond. It reminds us that our cosmic knowledge, though vast and growing, remains fundamentally limited by our position within the universe we seek to understand. The cosmos we study is always the cosmos we can see a reflection, framed by the maximum distance from which light has had time to reach us since the beginning of time. In our journey across cosmic scales, we've explored how the universe reflects, remembers, and even observes itself through various physical processes. We've seen how light bends around massive objects, how the vacuum preserves quantum echoes, how galaxies illuminate themselves from within, and how the cosmos preserves its history in the light still traveling through space. Now we arrive at perhaps the most profound question of all. Could the universe, as a whole, ever truly know itself? This question takes us beyond conventional science into philosophical territory, yet it remains grounded in the physical reality we've been exploring. It invites us to consider what it would mean for a system as vast and complex as the cosmos to possess something analogous to self-awareness or self-understanding, not in a mystical sense, but as an emergent property of its interconnected processes. The concept of a self-aware universe immediately triggers associations with consciousness, that mysterious phenomenon through which humans and possibly other creatures experience and model their surroundings. Consciousness remains one of the greatest scientific puzzles, with no consensus on how exactly it emerges from physical processes in the brain. Yet we know it exists, at least in ourselves, and its presence in the universe raises profound questions about the relationship between awareness and physical reality. Is it possible for a system to be fully self-aware? Even in humans, self-knowledge is partial and limited. We can never fully observe our own minds from the outside, never completely step back from our thoughts to examine them objectively. Our self-awareness operates through models and representations, simplified versions of reality constructed by neural processes we largely don't consciously perceive. Complete self-knowledge may be intrinsically impossible for any system that's part of what it's trying to understand. This limitation becomes even more pronounced when we consider the universe as a whole. If the cosmos were somehow to know itself, this knowledge would have to exist within the universe, as part of the system being known. Unlike external observers who can examine objects from outside, the universe cannot step outside itself to gain an objective perspective. Any cosmic self-knowledge would necessarily be embedded within the very reality it seeks to understand. Yet despite these inherent limitations, the universe exhibits remarkable self-reference through the laws and patterns that govern its behavior. The conservation laws we discussed earlier, conservation of energy, momentum, angular momentum, represent ways the cosmos maintains consistency with itself across time and space. These aren't arbitrary rules imposed from outside, but emergent properties of the universe's own symmetries. In this limited sense, the universe already knows its own structure through the mathematical relationships that maintain its coherence. On a deeper level, the universe may carry self-reflective patterns through the phenomenon of information processing. Information, in the physics sense, relates to the distinction between different possible states of a system and how those states evolve over time. The universe processes information constantly as particles interact, fields fluctuate, and complex systems evolve according to physical laws. This processing doesn't require consciousness, but represents a more fundamental form of knowing, the registration and transformation of differences that make a difference. When a photon is absorbed by an atom, information about the photon's energy is registered in the atom's new state. When a planet's orbit changes in response to gravitational influences, it encodes information about the distribution of mass in its vicinity. When a galaxy forms stars in response to density waves propagating through its spiral arms, it processes information about its own structure. These are not conscious acts, but physical processes that register and respond to specific aspects of reality. The universe's capacity for information processing reaches extraordinary levels in certain systems, particularly in biological organisms, and especially in brains. The human brain, with its approximately 86 billion neurons forming trillions of connections, represents the most complex information processing system we know of. Through this intricate network, humans construct internal models of the external world, recognize patterns, predict future events, and reflect on their own existence. This capacity for reflection and model building exists on a spectrum. Simple feedback mechanisms in physical systems represent a basic form of self-reference. Biological regulation through homeostasis involves more complex self-monitoring. Animal cognition introduces the ability to form internal representations of the environment. Human consciousness adds explicit self-awareness and the ability to contemplate abstract concepts, including the nature of the universe itself. Each level emerges from the physical processes of the level below, creating increasingly sophisticated ways for the universe to model aspects of itself through its components. In this view, human consciousness isn't separate from cosmic processes, but represents an advanced form of the self-organizing, self-referential dynamics that operate throughout nature. When we contemplate the cosmos, we are, in a very real sense, the universe contemplating itself through one of its most complex subsystems. Could more advanced forms of self-reference emerge in the future? Some theorists have speculated about the possibility of global brain scenarios, where networked intelligence, whether human, artificial, or some hybrid, creates unprecedented capacity for information processing and self-modeling. Such networks might develop forms of awareness fundamentally different from individual human consciousness, potentially enabling more comprehensive modeling of physical reality. Others have explored the concept of Jupiter brains, or Matryoshka brains, hypothetical megastructures that would harness the energy of stars to power vast computational systems. Such structures could theoretically process information at scales far beyond current technology, perhaps modeling increasingly larger portions of physical reality with greater precision. While such concepts remain speculative, they suggest potential pathways for the universe's self-knowing capacity to expand beyond its current limits. The theoretical physicist John Wheeler captured this perspective in his concept of the self-excited circuit, where observers emerge from the universe and then, through observation, give definition to the universe from which they emerged. In Wheeler's view, the universe requires observation to transform quantum possibilities into definite outcomes. creating a loop where the cosmos produces beings capable of observing it. And those observations in turn help determine which potential reality becomes actual. This loop doesn't imply conscious design or purpose, but emerges naturally from the universe's fundamental properties. The same physical laws that govern particle interactions also govern the formation of stars, planets, and eventually life and intelligence. The capacity for observation and model building isn't something imposed on the universe from outside, but a natural development of its inherent information processing potential. The emergence of science itself represents a remarkable advance in the universe's self-knowing capacity. Through scientific investigation, observation, and theory building, humans have constructed increasingly accurate models of cosmic reality across scales from the subatomic to the galactic. These models aren't perfect, they remain limited by our observational capabilities, cognitive biases, and the inherent complexity of the phenomena being studied, but they represent the most comprehensive and precise self-model the universe has yet developed, as far as we know. Consider the extraordinary arc of cosmic self-knowledge represented by modern cosmology. Through systematic observation and mathematical modeling, the universe via human science has reconstructed its own history from the first fraction of a second after the Big Bang to the present day. It has mapped its large-scale structure across billions of light years, identified its major components, normal matter, dark matter, and dark energy, and projected its likely future evolution. Though this knowledge exists only within a tiny fraction of the cosmos, the scientific community, on one small planet, it represents a remarkable instance of the universe modeling itself. This self-modeling extends to the fundamental level as well. Quantum field theory and general relativity describe the basic fabric of reality with extraordinary precision, allowing the universe again, through human science, to model its own underlying structure. When physicists derive the properties of particles from the symmetries of quantum fields or calculate how mass curves spacetime, they're developing mathematical descriptions that capture essential aspects of how the universe operates at its most fundamental level. Yet despite these achievements, our scientific self-model of the universe remains incomplete. We haven't reconciled quantum mechanics and general relativity into a single coherent framework. We don't understand the nature of dark matter or dark energy, which together constitute about 95% of the cosmos's contents. We can't directly observe what happened before the cosmic microwave background formed, or what lies beyond our cosmic horizon. The universe's self-knowledge through human science, though remarkable, is still partial and evolving. This incompleteness raises the question of whether complete cosmic self-knowledge is even possible in principle. Gödel's incompleteness theorems in mathematics suggest that sufficiently complex formal systems cannot be both complete and consistent. They contain truths that cannot be proven within the system itself. Similarly, the universe may contain aspects of reality that cannot be fully modeled or known from within, fundamental limits to self-reference that no amount of scientific progress can overcome. Information theory offers another perspective on these limits. The universe contains a finite amount of matter and energy within our cosmic horizon, which places an upper bound on the information it can physically encode. Any model of the universe would itself require physical resources to store and process, resources that are part of the very system being modeled. A complete and perfect self-model would require more resources than are available in the system itself, a logical impossibility that suggests fundamental limits to cosmic self-knowledge. Yet even with these limitations, the universe may still develop increasingly comprehensive self-understanding through its most complex subsystems. Just as human science has progressed from simple observations to sophisticated theories that explain diverse phenomena with mathematical precision, future developments, whether through advanced artificial intelligence, enhanced human cognition, or forms of intelligence we cannot yet imagine, might extend our cosmic self-model to encompass more of reality with greater accuracy. This progression suggests a fascinating possibility that the universe's self-knowing capacity might be an evolving property, something that develops and expands over cosmic timescales. Rather than asking whether the universe could ever know itself completely, perhaps we should consider how its self-knowledge might grow and change through the emergence of increasingly sophisticated information processing systems. From this perspective, conscious life could indeed be part of how the universe comes to know itself, not as the endpoint of a teleological process, but as an emergent phenomenon that creates new possibilities for cosmic self-reference. When conscious beings observe and model the cosmos, they're not doing something separate from cosmic processes, but extending the universe's intrinsic capacity for self-organization and information processing to new levels of complexity. The anthropologist and systems theorist Gregory Bateson defined information as a difference that makes a difference. By this standard, conscious observers represent a profound innovation in how the universe processes information. Unlike simple physical interactions, where information is encoded implicitly in state changes, conscious minds can explicitly model aspects of reality, identify patterns across different domains, and even contemplate their own existence. This creates not just new information, but new kinds of information abstractions, theories, and self-reflective models that weren't present in simpler systems. This capacity for abstraction allows conscious observers to transcend local perspectives in ways that simple physical systems cannot. While a particle can only know its immediate interactions, and a planet can only respond to nearby gravitational fields, a conscious being can construct models of the entire observable universe, spanning billions of light years and billions of years of cosmic history. Though these models remain limited and approximate, they represent a qualitative leap in the universe's self-referential capabilities. The development of mathematics further extends this leap. Mathematical structures allow precise description of patterns and relationships that underlie diverse physical phenomena, from the orbits of planets to the interactions of quantum fields. When physics discovers that the same equations describe apparently different systems, it reveals deep connections that simple observation could never detect. This mathematical self-modeling gives the universe, through conscious observers, a way to recognize its own underlying unity across diverse manifestations. Language adds another layer to this cosmic self-reference. Through symbolic communication, conscious beings can share their models and observations, creating collective knowledge that transcends individual limitations. The scientific enterprise itself, with its methods for systematically testing ideas against reality, represents a social technology for refining our cosmic self-model, gradually correcting errors and extending its scope and precision over generations. Technology further enhances these capabilities. Telescopes let us observe distant galaxies our eyes could never see. Particle accelerators reveal subatomic structures, invisible to direct perception. Computers process vast datasets and simulate complex physical systems, extending our cognitive capabilities far beyond their biological limits. Each technological advance creates new ways for the universe, through its conscious components, to observe and model aspects of itself previously inaccessible. This progressive enhancement of cosmic self-modeling suggests that the universe's self-knowing capacity might continue to develop in ways we cannot yet imagine. Future technologies, whether based on quantum computing, artificial general intelligence, brain-computer interfaces, or concepts beyond our current understanding, could create unprecedented capabilities for observing, modeling, and understanding cosmic processes across all scales. Some transhumanist thinkers have speculated about the possibility of a technological singularity, a hypothetical point where artificial intelligence surpasses human capabilities and begins to improve itself, potentially leading to an intelligence explosion. While such scenarios remain speculative, they suggest how the universe's self-knowing capacity might undergo sudden, dramatic expansion through the emergence of new forms of intelligence built on, but qualitatively different from, human consciousness. Even without such dramatic developments, the gradual accumulation of scientific knowledge represents an ongoing expansion of cosmic self-reference. Each new discovery, whether about the early universe, the nature of black holes, the structures of distant galaxies, or the fundamental forces that shape reality, adds another piece to the universe's self-model, constructed through the efforts of countless researchers over generations. This scientific self-model extends beyond passive observation to active manipulation. Through experiments, we don't just observe reality, but interact with it, testing our models against the universe's responses. When physicists at CERN collide particles at near-light speeds, they're not just watching nature, but engaging in a kind of conversation with it, asking questions through experimental setups and receiving answers through the resulting phenomena. This dialogic quality enhances the depth and precision of our cosmic self-model. The philosophical implications of this perspective are profound. If conscious observers represent the universe's way of knowing itself, then our scientific quest to understand reality isn't just a human activity, but a cosmic one, the universe, through one of its most complex subsystems, constructing an increasingly comprehensive model of its own nature and history. Our philosophical and scientific questions become the cosmos questioning itself. Our discoveries become the universe, discovering its own nature. This doesn't mean the universe has a unified consciousness or intentionality in any conventional sense. The self-knowing we're discussing emerges from localized processes, particular brains, in particular bodies on particular planets, not from some mystical cosmic mind. Yet these localized instances of awareness aren't separate from cosmic reality but integral components of it. Special arrangements of matter and energy that create new possibilities for information, processing, and self-reference. The universe's self-knowing capacity extends beyond scientific understanding to encompass aesthetic and emotional responses as well. When we experience awe at a starry sky, wonder at the complexity of living systems, or deep connection with the cosmos through contemplative practices, we're engaging with reality in ways that complement and enhance our conceptual understanding. These experiences represent another dimension of cosmic self-reference, one that recognizes value and meaning as emergent aspects of reality. Art and literature provide yet another avenue for cosmic self-reference. When artists create works inspired by natural patterns, scientific discoveries, or cosmic themes, they're translating aspects of reality into new forms that highlight particular qualities or relationships. A painting of a nebula, a symphony evoking celestial motion, or a poem reflecting on quantum entanglement each represents the universe exploring its own nature through human creativity, revealing dimensions of reality that purely analytical approaches might miss. Spiritual and contemplative traditions also contribute to this cosmic self-reference, though in ways that often differ from scientific approaches. Many mystical experiences involve a sense of direct connection with the cosmos, a dissolution of the boundary between self and world that can generate profound insights about the nature of reality. While such experiences don't replace scientific understanding, they complement it by providing different modes of knowing: intuitive, holistic, and experiential rather than analytical and theoretical. This multiplicity of knowing modalities suggests that the universe's self-reference isn't limited to a single approach or perspective. Just as light can be understood as both wave and particle depending on the experimental context, reality might require multiple, complementary frameworks to be more fully understood. The universe might know itself not through a single, unified model but through diverse approaches that capture different aspects of its nature. The question of whether the universe could ever know itself thus transforms from a binary yes, no, to a matter of degree and kind. The cosmos already knows itself in limited ways through the physical processes that maintain its coherence across time and space. It knows itself more explicitly through the emergence of life and consciousness, particularly through the scientific, philosophical, artistic, and contemplative approaches that humans have developed to understand and relate to reality. This self-knowing capacity continues to evolve as our scientific knowledge expands, our technologies advance, and our philosophical frameworks develop. Future forms of intelligence, whether human, artificial, or some integration of both, might extend cosmic self-reference in directions we cannot currently imagine, creating new ways for the universe to model and understand its own nature. Yet despite this ongoing evolution, complete self-knowledge likely remains an unreachable limit rather than an achievable goal. The universe may continue to know itself better without ever reaching perfect self-understanding, an asymptotic approach to a horizon that recedes as we advance toward it. Each new discovery reveals new questions. Each answered question spawns new mysteries in an endless dialogue between the cosmos and its conscious components. As you drift towards sleep tonight, consider your place in this cosmic self-reference. Your consciousness, with its capacity for wonder, curiosity, and understanding, represents one of the ways the universe knows itself. Your questions about reality are the cosmos questioning itself through you. Your insights, however modest, contribute to the universe's ongoing exploration of its own nature. In contemplating the stars, you participate in a profound cosmic process matter that has evolved to the point where it can wonder about its own origins and destiny, the universe reflecting upon itself through the remarkable phenomenon of conscious awareness. The journey we've taken together across these chapters has spanned scales from the quantum to the cosmic, exploring the many ways in which the universe observes, reflects, and potentially knows itself. We've seen how light bends around massive objects, how vacuum fluctuations preserve quantum echoes, how galaxies illuminate themselves from within, and how the cosmos encodes its history in radiation still traveling across space. Each of these processes represents a way in which the universe maintains coherence and preserves information, a kind of cosmic memory written in light, gravity, and the very fabric of space-time. As our exploration concludes, we return to the image with which we began, the sky that looks back at itself. This isn't merely a poetic metaphor, but a description of physical reality. The universe really does observe itself through countless interactions between its components. Particles register the states of other particles. Atoms absorb and emit photons that carry information across vast distances. Galaxies shape and are shaped by the cosmic web of which they're part. And conscious beings, emerging from this intricate dance of matter and energy, construct increasingly sophisticated models of the reality from which they arose. This cosmic self-observation operates across all scales simultaneously. At the quantum level, the vacuum seethes with virtual particles that preserve traces of past events in subtle fluctuations. At the astronomical scale, gravitational lensing allows the universe to see around its own corners, revealing structures that would otherwise remain hidden. At the cosmic scale, the expansion of space itself creates a natural horizon that frames our observable universe, defining what we can know about the cosmos through direct observation. Time adds another dimension to this self-referential quality. The finite speed of light transforms space into a temporal record, with more distant regions showing earlier cosmic epochs. The ancient light of the cosmic microwave background reveals the universe as it appeared just 380 years after the Big Bang. Light from distant galaxies shows them as they were billions of years ago. The universe preserves its own history in the radiation that continues to travel through space, carrying information about events long past to observers who might intercept it in the distant future. Perhaps most remarkably, the universe has evolved systems complex enough to construct explicit models of cosmic reality. Through science, philosophy, art, and contemplative practice, conscious beings explore the nature of existence, building frameworks that capture aspects of how the universe operates across all scales. When we observe the night sky with understanding, recognizing the nuclear processes powering distant stars, or the expanding space that redshifts faraway galaxies, we participate in a profound cosmic feedback loop the universe, through one of its most complex subsystems, comprehending its own nature and history. This self-knowing quality doesn't require mystical or supernatural explanations. It emerges naturally from the properties of physical reality, the conservation laws that maintain consistency across time and space, the information processing capacity inherent in complex systems, the feedback loops that connect different scales and processes. The universe observes itself not through some cosmic consciousness separate from natural phenomena, but through the innumerable interactions between its components, from quantum fluctuations to conscious contemplation. The sky is not just where we look, it is what we are inside of. We exist within the universe, not separate from it. The atoms that form our bodies were forged in ancient stars. The energy that powers our thoughts traces back to the Big Bang. The light that carries information to our eyes has traveled across vast reaches of space, bringing messages from distant regions and earlier times. We are not isolated observers of cosmic processes, but integral participants in them, nodes in the vast network of interactions through which the universe registers and responds to its own state. This perspective transforms our relationship with the cosmos. We're not alienated observers of an indifferent universe, but expressions of its intrinsic tendency toward complexity and self-reference. Our consciousness, with its capacity for wonder, curiosity, and understanding, represents one way the universe explores its own nature. Our scientific discoveries aren't just human achievements, but cosmic ones, the universe, through evolved complexity, uncovering the principles that have guided its development since the beginning of time. The universe holds our light, the electromagnetic radiation emitted by our planet, our civilization, our individual body aces. It travels outward at the speed of light, carrying information about Earth to increasingly distant regions of space. It holds our past in the light that has already departed, the gravitational waves we've generated, the particles we've set in motion, and it holds our questions, our wonder, our attempts to understand, if not as concrete physical phenomena, then as patterns of information processing that represent another way the cosmos explores its own potential. It curves, it expands, it carries echoes older than stars and reflections brighter than we can measure. The universe isn't static but dynamic, constantly changing while preserving certain fundamental symmetries and conservation laws. It curves not just in the geometric sense described by general relativity, but in the way information flows through feedback loops, with causes producing effects that become causes for new effects. It expands not just as space stretches between galaxies, but as complexity emerges from simplicity, creating new possibilities for interaction and self-reference. And though it may never truly look back, it offers us something almost the same, a memory so vast, it feels like recognition. The universe doesn't possess a unified consciousness that could look back in any conventional sense. Yet its capacity to preserve and process information creates something analogous to memory patterns that persist across time, relationships that maintain coherence despite constant change, structures that encode their own history, and the principles that shape them. When we recognize these patterns, when we discern the laws that govern cosmic evolution, we participate in a form of remembering that transcends individual consciousness. Sleep now, beneath the sky that remembers. As you drift toward unconsciousness, consider the continuous interactions between your body and the cosmos. With each breath, you exchange atoms with your environment. With each heartbeat, gravitational waves imperceptibly tiny but mathematically precise propagate outward at the speed of light. Your body radiates infrared light that carries information about your temperature and form. You exist in constant dialogue with the universe, not as something separate from cosmic processes, but as a unique and temporary configuration of them, a pattern of matter and energy that exchanges information with its surroundings in extraordinarily complex ways. And wonder, just for a moment, if it too wonders about you. Not in the anthropomorphic sense of a cosmic consciousness similar to human awareness, but in the sense that your existence represents one way the universe explores its own potential. Your capacity for wonder, that distinctive cognitive emotional response to what is sublime, mysterious, or profound, isn't something alien to cosmic reality, but an expression of it, a particular manifestation of the universe's intrinsic tendency toward complexity and self-reference. The night sky above you contains stars whose light has traveled for years, decades, centuries, or millennia to reach your eyes. Their photons, which began their journeys long before you were born, complete their cosmic voyages on the retinas of your eyes, triggering electrochemical reactions that your brain interprets as points of light against darkness. This interaction between ancient starlight and evolved consciousness represents another way the universe connects with itself across vast distances of space and time. Beyond what we can see with our eyes, or even our most powerful telescopes, the cosmos continues filled with galaxies, black holes, mysterious dark matter, and perhaps forms of complexity we haven't yet imagined. Our cosmic horizon limits what we can observe directly, but it doesn't limit what exists. The universe extends far beyond the boundary of our observable region, possibly infinitely, with the same fundamental laws creating endlessly varied arrangements of matter and energy throughout unobservable realms. Within this vast, ancient, evolving cosmos, consciousness emerges not as something separate from natural processes, but as a particularly intricate expression of them. When you wonder about the stars, you aren't an isolated observer contemplating something external to yourself. You're a configuration of the universe, wondering about other configurations of itself, a pattern of matter and energy reflecting on the larger patterns of which it's part. This intimate connection doesn't reduce the wonder of existence, but enhances it. The universe isn't just the setting for our lives, it's the very substance of them, the source of every atom in our bodies, every photon that reaches our eyes. every possibility available to our briefly flickering consciousness. We aren't alienated observers, but integral participants in cosmic evolution, temporary but genuine expressions of the universe's capacity for complexity, awareness, and self-reference. As you fall asleep beneath the sky that remembers, carry this perspective with you. You are not apart from the cosmos, but a part of it, not separate from its processes, but an expression of them. Your consciousness, with its capacity for wonder, represents one way the universe explores its own nature. Your questions about reality are the cosmos questioning itself through you, and in the vastness of space and time, this moment of awareness, however brief in cosmic terms, represents something extraordinary. The universe evolved to the point where it can contemplate its own existence, wonder about its origins and destiny, and recognize the profound interconnections that bind all things into a coherent whole. This is the gift and the challenge of human consciousness, to recognize both our cosmic insignificance in terms of size and duration, and our cosmic significance as expressions of the universe's capacity for self-awareness. We are tiny specks in an almost unimaginably vast cosmos, yet we embody a form of complexity that allows the universe to know itself in ways that would be impossible without conscious observers. Our brief lives represent fleeting configurations of matter and energy, yet through them, the cosmos achieves something remarkable: explicit self-reflection, the ability to construct models of reality that capture aspects of how the universe operates across all scales. Sleep now, cosmic traveler. Rest your body, that temporary arrangement of stardust that has, through billions of years of evolution, developed the capacity to wonder about the stars from which it came. Dream beneath the sky that has witnessed the entire history of our planet, and that carries within its darkness the light of countless worlds. And perhaps, in that liminal space between wakefulness and sleep, you might feel for a moment what poets and mystics have intuited throughout human history: that profound connection between your consciousness and the cosmos that gave rise to it, the universe, knowing itself through you.